and good afternoon and good evening, everyone, and welcome to our webinar today on POPs in plastics. It is a great pleasure to see you all here. My name is Martin Scheringer. I'm the chair of the IPCP, the International Panel on Chemical Pollution. And I will just say a few words at the beginning, also together with Roland, and then we can get started with the actual content of the webinar. The webinar today is part of a new project on POPs in plastics and their sampling and monitoring. And Roland Weber leads this project. The project is carried out within a larger JEF-funded project on continuing regional support of the POPs Global Monitoring Program under the Stockholm Convention. The IPCP supports Roland with the administration and implementation of the project, and we thank Roland very much for all his work as a leader of the project. As you can see now on this next slide, there will be a series of webinars. So there will be 3 blocks. Yesterday and today is the first block, where we have speakers who share a lot of knowledge about POPs in general and POPs in plastics. And it's really about the background and establishing background knowledge about POPs in plastics. Then there will be 2 more blocks on the sampling of plastics and how to then prepare the samples for POPs measurements. And then in the third part, 1 or 2 webinars on the actual sample preparation and analysis and measurement of POPs in these samples from plastics. The exact dates for these 2 other blocks have not yet been set, but most likely they will take place in the second half of May. And that would then still be for the INC2, the second meeting of the Intergovernmental Negotiating Committee for the new plastics treaty. Finally, all of this work or the webinars are part or an element of a larger project, as I said, and there are 2 more activities in that project. One activity will be a report that highlights what's known about POPs in plastics and also highlights current knowledge gaps about POPs in plastics. And then the third activity will be actual sampling and measurement of a range of POPs in plastic samples from different UN regions, Africa, Asia, and Gulag, with laboratories in Japan, Germany, and Thailand. That will then be the overall activity in the project, and the project will be concluded, I think, by the end of June or July. And with this, I would like to wish you all a productive and informative webinar today and hand over to Roland for an overview of the day. Thank you.
Yes, thank you very much, Martin. Yeah, good day to everybody. We had yesterday a real good first day webinar. We already have the Zoom link, which we will share later. Maybe 2 sentences also about my person. Yeah, I'm a member of International Panel on Chemical Pollution. This means continuing research with different research groups. But my main work is consulting to UN organizations and environmental and ministries for the implementation of the Stockholm Convention, which I'm doing more than 15 years, including also supporting the Basel, Rotterdam, and Stockholm Convention Secretariat with different guidance documents. So the program of today is that we will look to the different POPs groups and their relationship to plastic. So we will start with the brominated POPs in respect to plastic and recycling, going then to the chlorinated, short-chain chlorinated paraffins and medium-chain chlorinated paraffins. We will then have a look to the POP candidate Dechlorane Plus and how it relates to plastics and the suggested exemptions, because Dechlorane Plus is not yet listed, will be listed next month. And also we will do that for the POP candidate UV 3 to 8. And finally, we also will have a look to the fluorinated POPs and have a presentation about their relationship to polymers and plastics. The first presentation will be from me on understanding brominated POPs, the PBDEs, the hexabromocyclododecan, hexabromobiphenyl in plastics. So yesterday we already highlighted 9 of the new listed POPs are additives in plastics, and 5 of these POPs are brominated flame retardants. Here the commercial penta BDE, the commercial octa BDE, or let's say the 2 homologues hexa and hepta bromodiphenyl ethers from the commercial octa BDE ethers have been listed. Then decabromodiphenyl ethers is listed, and hexabromobiphenyl and hexabromcyclododecan. So decabromodiphenyl ether and hexabromcyclododecan receive exemptions for continuing production in their listing, and the deca BDE is still produced. So brominated flame retardants, including the polybrominated diphenyl ethers, have been widely used here as additive flame retardants in plastic since the 1970s, including synthetic fibers and plastics in electronics, vehicles, and buildings. When we look to more details of the decabromodiphenyl ethers, you can always get details on the listing, which includes good background information on the Stockholm Convention website. Here, the different documents from POP Reviewing Committee. So the decabromodiphenyl ether was the PBDE with the highest production volume, 1.6 million tons. And we have a still ongoing production in China. And the production volume is not known, but it is most probably less than 10,000 tons. So when decabromodiphenyl ether was listed in 2017 in the Stockholm Convention, it has been listed with a range of exempted uses, and several countries have registered for exempted uses. So therefore, yes, it is still produced and also used in a range of countries in production. These exemptions were textiles that require anti-flammability characteristic, excluding clothing and toys. Then additives in plastic housing of parts used in heating, home appliances, iron, immersion heaters, and so on. So it is still allowed in electronics. Then also polyurethane foam for buildings insulation is exempted in the listing. Parts for the use in vehicles, which are then further specified in the Stockholm Convention. You can have a look at the Stockholm Convention text, and also for aircrafts, certain spare parts for aircrafts. When we look to the listing of the tetrabromodiphenyl ether, pentabromodiphenyl ether of commercial pentabromodiphenyl ether, there was no exemption for production, and there was also no exemption for use. The only exemption for the listing in 2009 was that it may allow recycling of articles that may contain chemicals and that may contain commercial penta-BDE. So in the listing, the parties, let's say, understood that if we listed without the exemption for recycling, maybe the recycling for certain productions like electronic waste plastic might not be allowed. Then the listing, Markus, your sound is not muted. You need to mute your sound. We have the hexabromocyclododecan was listed in 2013. So this was also listed with exemption of further production and use. And here the exemption was for expanded and extruded polystyrene for building insulation. And the production continued, especially in China, until end of 2021. And now this production also has stopped, and there is no exemption for production anymore. When we look to the health effects, which I highlighted already yesterday, we have for PBDEs a range of endocrine disrupting effects, reproductive effects, diabetes, effects on child's development, especially here the commercial penta-BDE homologues were associated with the neurodevelopmental deficits. So children with higher PBDE levels showed here 5 to 8 points lower IQ scores. Herbstman et al. In 2010 showed that. And also similar effects were found in Dutch children's studies, where the prenatal exposure of penta-BDE and also hexabromocyclododecan was associated with adverse effects of motor, cognitive, and behavioral outcomes. So the health cost here was assessed here in the United States for the PBDE, and this IQ loss and intellectual disability were estimated to cost $266 billion per year. And for Europe, it was estimated to 9 billion euro per year. Decabromodiphenyl ether has a lower toxicity, but it can degrade to the lower brominated and more toxic PBDEs, and also has a strong potential to form brominated dioxins, and especially the furans, which have a similar toxicity like the chlorinated dioxins. A very good study which shows the exposure pathways, or indicates the exposure pathways for the PBDEs, is the study on blood levels of PBDEs in Wisconsin cohort study. What we see there is that the PBDE levels in blood had about 2 orders of magnitude differences between individuals. Yeah, in total, 44 participants were analyzed, 29 men, 15 women. They were analyzed twice, and you see that there were certain individuals with very high levels and certain individuals with quite low levels. Yeah, so what you see there, that this cannot be explained, for example, by exposure from normal food. Yeah, so when we look to the PCBs, for example, we normally do not have a difference of more than a factor of 10. Yeah, so in this study, they also looked to different individuals which were higher exposed, and the likely source of exposure were treated pillows, vehicles, or furniture. Yeah, so you see here the real high exposure to PBDEs come from these PBDE treated products at home, or also the cars. So therefore, when you look to the life cycle of PBDEs here, from emission sources, environmental transport, and exposure sources, we see that in addition to accumulation here in the environment and in food and food ingestion, yeah, which is the major exposure pathway, for example, for dioxins, 90%, or for PCB, normally 90%. For the PBDEs, we have a very strong exposure from these products which have been treated, especially with the penta-BDE. And as I will show later, also there is exposure from recycled products. The relevance, especially for the management of plastic and the large material flows and the recycling flows, depend on the total volume of the use of a certain POP and the time of use of a certain POP. And we have here for the PBDEs large use, like for the deca bromodiphenyl ethers, there was a use of 1.6 million tons in the past, from the 1970s, increasing to the 1980s, 2000s, with the largest use between 2000 and 2010, and then again a decrease of use. In total, when you also include the octa BDE and the penta BDE, we have about 1.9 million tons of PBDEs which have been produced. And when we assume a rough average amount of 10%, we can conclude that about 19 million tons of POP or PBDE containing plastics have been produced in the past, which need to be managed, and partly already have been managed because, yes, the PBDE, which have been used in the 1970s, already have entered largely to the end of life, while the more recent uses are still in use and are in the recycling flows. Also, for hexabromocyclododecan, the total production was 0.7 million tons. And production was, when you look here to the time in the different decades of hexabromocyclododecan, we have all production started in the 1960s, 70s, 80s with increase, but the highest use also for this compound was in the 2000s and until now, until 2020, until China stopped production. When we assume here, especially for the EPS, XPS, where we have 90% of all the hexabromocyclododecan used in the past, average concentration of 1.5% of hexabromocyclododecan, we can conclude that we have about 42 million tons of EPS and XPS, which is still largely present in insulation foam because of the long term use of insulation foam. I will come later to that. The last brominated flame retardant which have been listed in the Stockholm Convention is hexabromobiphenyl. This has only been produced to about 5,350 tons in the United States between 1970 and 1976. So most of these products have largely been disposed in the past 50 years. And maybe only some classic cars from United States produced in the 1970s might contain this hexabromobiphenyl. So therefore, normally you do not hear much about hexabromobiphenyl. Also, we do not really find it in human milk studies. So here, the human milk study, the detection levels were it was not detected, so it was the concentration were below the detection level of hexabromobiphenyl. So this shows at least that for the general population in the world, it is not relevant, also not for the material and recycling flows. The major use of decabromodiphenyl and commercial octabromodiphenyl were in all major uses of these polymers, mean electronics, construction, the transport sector, and the textile sector. You see here, this is a study from Abbasi et al. From 2019 in Environmental Science Technology, where they have made an estimate for the different PBDE commercial uses, what were the major application area. For octa BDE, the major use, 40%, were in electronics, and even distribution they estimated for construction and transport, foam and carpets, lower amount in textiles. When we look to the decabromodiphenyl ether, they also estimated that the highest use was in electronics, about 30% of deca BDE use, 20% in construction, 15% in transportation, and also 25% in foams and carpets, yeah, but normally this also were used, for example, in transport and in buildings. So normally I do a categorization of electronics, construction, and transportation. And also when you look here to the textiles, 15% part of this textile is also used in the transport sector. For pentabromodiphenyl ether, it is different. The major use of pentabromodiphenyl ether was in polyurethane foam, and a major part of this polyurethane foam has also been used in transport and in construction. Yeah, so also here where they highlighted 50% has been used in foam and carpets. This overall need to be added also to the construction sector and to the transport sector. And what should be highlighted is that 90% of the commercial penta-BDE have been used in the United States, and I have shown yesterday that this is also reflected in the human milk levels, where the United States has, let's say, 100 to 20 times more of this penta-BDE in human milk compared to other countries, to most other countries. For the hexabromocyclododecan, the major use, 90%, have been in construction. And the second most used have been in textiles, but also this was less than 8%. And other uses, like in transportation, was less than 3% of total hexabromocyclododecan use. And also for electronics in high impact polystyrene, the use of HBCD was less than 3% of the global HBCD production. Interesting data set, because one problem is also that often we do not understand for individual producing countries what was the time of use, and this was actually different for different countries. The only real good data set we have from Japan. And here for Japan, you see that, for example, for commercial penta-BDE, Japan used commercial penta-BDE mainly in the 1980s, and already in 1991, the commercial penta-BDE use in industry has been stopped in Japan. For commercial octa-BDE in Japan, the use has also already been reduced in the 1990s and has been stopped before 2000. For commercial deca-BDE, yeah, commercial deca-BDE has substituted here commercial penta-BDE and commercial octa-BDE in different uses like electronics and vehicles. But also what you see here, the use of commercial deca-BDE already had its peak in the 1990s in Japan and has decreased since then. And in Japan in 2017, the use of commercial deca-BDE has been phased out. For hexabromocyclododecan, we see an increasing trend since the 1980s in Japan. But then when hexabromocyclododecan came into the POP reviewing committee, Japan already reduced the use of hexabromocyclododecan. And when hexabromocyclododecan has been listed, Japan did not ask for a production and use exemption. And what you see here, they stopped in 2013 when hexabromocyclododecan was listed in the Stockholm Convention. Yeah, also here you really see that these conventions can work globally. The PBDEs have been produced longer. I mean, penta and octa BDE, for example, in the United States and in Israel until 2004. Also, China has produced commercial penta BDE until 2003 or 2004. But this have then also been stopped in those countries. And what I said, commercial hexabromocyclododecan has been produced until 2021. So therefore, today, only decabromodiphenyl ether is still produced at reducing levels in China. Another interesting time trend for you to understand the PBDEs in plastics and in products are material and substance flow analysis. And here, this is a material and substance flow analysis of decabromoDiphenyl ethers in United States and Canada. And what you see here, yes, the production and the use is here reflected also in the United States. We have an increasing use of DKBDE here until the mid of 2000, yeah, and already 2006-07 we have a decreasing use of DKBDE in products. And interesting is then to look to the individual uses, yeah. So the major use also for the United States was here in electronics. And what you see here in the products, already we have a decrease in the products from 2005 on, and because the products have a different service lives, with relatively short service lives of electronics compared, for example, to automotive. You see that the presence of DKBDE in products of electronics is decreasing, and already in 2020 it is estimated that only a small share of electronics containing DKBromoDiphenyl ethers are present in the United States. Yeah, while for vehicles here the service life is longer, and therefore still more DKBromoDiphenyl ethers is estimated to be present in vehicles in the United States compared to electronics. This is different for developing countries, and therefore we have done some studies of material and substance flow analysis of DKBromoDiphenyl ethers in Nigeria to understand how the time development is there. So we have first estimated from the total imports of electronics, but also of vehicles, the inflow to Nigeria in total between 1980s to 2020, about 1,400 tons of DKBromoDiphenyl ethers entered Nigeria in vehicles. And from these 1,400 tons, still about 1,000 tons is present in registered vehicles. Yeah, only about over the last 40 years from the vehicles which were coming into Nigeria, about 380 tons were estimated to have reached end of life. Yeah, and also we had a look to the end of life management of vehicles in Nigeria, and we saw that we estimate that around 250 tons were disposed to landfills. We have also considerable share of open burning, so about 60 tons of DKBromoDiphenyl ethers from this end-of-life vehicle polymers were openly burned. And interestingly, spare parts of cars are reused in Nigeria. So there is an estimate that about 77 tons of DKBromoDiphenyl ethers entered again the reuse sector, and partly it has been reduced, and partly about 50 tons of DKBromoDiphenyl ethers is still in polymer parts in companies. Yeah, and this you need to see when you look to end-of-life vehicles. Normally these end-of-life vehicles are just often put to backyards, yeah, where they are used then over years and even decades for the spare parts. Yeah, so therefore it is estimated that a relatively high share of this DKBDE from end of life is in the polymer spare parts, and only 19 tons have been used again or sold again to vehicles. And when you do a projection with a dynamic material substance flow analysis for Nigeria, which has been done by Professor Babayemi, you see that these long service life of vehicles in here in Nigeria, but this is likely similar in other countries in Africa, results that the presence of DKBDE actually is still increasing in Nigeria. Yeah, so this is very different to the United States, yeah, or other countries like Japan also. Yeah, for Japan also, most of the DKBDE is already gone and has been exported in vehicles here from United States, from Europe, from Japan, and is still incoming into developing countries. And for Nigeria, the estimate from our modeling, which is a relatively robust modeling, we have done this study together with the Technical University of Vienna, which have one of the most robust material and substance flow analysis methodologies. We see that the peak of decabromodiphenyl ethers for Nigeria is reached around 2030. Yeah, and from there, then overall in 2030, we do not have new incoming vehicles with decabromodiphenyl ether because, yes, the major use of decabromodiphenyl ether was until 2017, also for vehicles. Yeah, and only then we have a decrease. Yeah, this means that for developing countries, decabromodiphenyl ethers here in polymers and plastics in vehicle will be relevant for the next decades to come. We have also done dynamic material and substance flow analysis for hexabromocyclododecan in construction sector with the Peking University, Professor Li and Professor Liu. I was also part of that team. And for this insulation foam, because of the longer service life compared to vehicles or electronics, we see that we have an increase of the use here until 2020, 2021, yeah, where we had the stop of hexabromocyclododecan, and only the waste management and the amount of EPS and XPS which comes in the waste is only now starting. Yeah, in our project where we have a destruction component, there was a discussion if we even have the 1,000 tons of EPS and XPS. Yeah, but then we see that waste will increase over the next decades. It is estimated that for China we have a peak of EPS, XPS in the waste flow by 2050, and still when we look forward to 2100, there will be still hexabromocyclododecan containing EPS and XPS in use coming into the waste management. Yeah, this means for the management of EPS and XPS in buildings, we have really to think not only in decades, but rather in a century and longer. So therefore, in our publication where we highlighted, let's say, this challenge with the flame retardant standard and the challenge also here of the materials coming here for the next decade in end of life, despite we have here the stop in the Stockholm Convention of these different chemicals. We have highlighted, yes, that this takes decades or even going to a century. And we have highlighted in that publication that if we do then additionally recycling of this material, of course, this will keep the materials and the POPs in plastics for even longer. So therefore, we really need to take care and look to the recycling cycles now and separate and phase out. And for this, we need to look to the three major use of the polymers in vehicles, electronics, and in buildings. When you look to the total amount of plastic and polymers used here for Europe, you see that about 20% has been used in buildings, 10% used in automotive, 6% in electronics. So in total, more than a third of all polymers and plastic categories can contain brominated flame retardants, yeah? While only a share of this, for sure, contains finally brominated flame retardants. For example, I think for electronics, it is overall less than 10% of the polymers in electronics which contain brominated flame retardants, yeah? But overall, when it comes to the end-of-life management, we have to look for all the polymers because we need to separate somehow. And when we look to these three relevant plastic and polymer use categories, we not only have here the brominated flame retardant, but we have also, yes, chlorinated flame retardants like SCCPs and MCCPs. We have Dechlorane Plus use, we will see in other presentations. And also we have the use of UV stabilizers 328, yeah? And then we have other chemicals of concern, which I introduced yesterday, like phthalates and bisphenols, in these categories. Yeah, so when we think about, let's say, the big management of these plastics in the next decades to come, we need to consider the different additives used, not only the POP PBDEs, but in this presentation, I focus on POP PBDEs. To the volumes. Here first, when we look to the end-of-life vehicles, today, or this was, I think, 2020, we have 1.3 billion vehicles. And it is expected that by 2050, we have about 2.2 billion vehicles. With the service life of about 20 years, this means we have about 65 million end-of-life vehicles per year. In each vehicle, we have in average approximately 200 kilograms of plastic polymers. This means that we have now about, in average, about 13 million tons of plastic and other polymer waste in end-of-life vehicles, which we need to manage. And a part of this waste, yeah, contain brominated flame retardants. At the moment, at the end of life vehicles, especially in industrial countries, we have shredding, and then we have one shredder fraction which contains plastic foams and rubbers, which contain relatively low content of brominated flame retardant and PBDEs, but let's say the whole contain these PBDEs. And at the moment there is a discussion and a thinking about this pre-separation, because many of the plastics, of course, in vehicles does not contain PBDEs or does not even contain brominated flame retardants, yeah? But at the moment, this is not pre-separated in most countries. We have a project in Ivory Coast, yeah, where I have proposed, together with the World Resource Forum and UNITAR, to look into this pre-separation and to think for if, let's say, improved recycling is possible when we do a manual dismantling before. Another problem is then when you have this shredder waste, it has a high halogen content, not only bromine, yeah, but you have also chlorine from the PVC. We have also some fluorine from the fluorinated polymers. So incinerators does not like it, yeah. Also, the cement industry does not like it because of these halogens. So also we have a challenge here in the thermal treatment of this plastic and polymers in the next decades to come. In Europe, we have an end-of-life vehicle directive, which since some years require recycling rates of 85% and recovery rates of 95%. So this requires that also some of the plastic and polymers is recycled, and it is interesting to look to the different countries in Europe, how they meet the recycling rates and how they meet the recovery rates, and a range of countries are struggling. So that's quite interesting for the world to look to the individual countries, what they are doing for that. When we look to plastics in e-waste, e-waste is the fastest growing waste stream in the world. The POPs are in the plastic fraction. We have in 2019 about 53 million tons of e-waste. It is estimated that by 2030, this will increase to 74 million tons per year worldwide. And when we look to the plastic fraction, here a study from Europe for the different electronic categories like coolers and freezers, or televisions, or other consumer equipment, we see that in average we have around 20% of plastic in electronics. This means that today, with the 53 million tons of e-waste, we have about 10.7 million tons of e-waste plastic per year, which we need to manage. Yeah, and this is increasing. Yeah, so we can estimate then by 2030 that we have then around 14 million or 15 million ton of plastics. Yeah, in 7 years. So only a fraction of this e-waste plastic, like I said, contain PBDEs. So it is challenging to recycle this plastic fraction, because it's quite heterogeneous. We have more than 10 different polymers used there. We have also a high halogen content overall. So therefore also we have a challenge in the thermal recovery of this fraction. And in the European Union, the V directive requires here a separation of V plastic for the brominated flame retardant fraction to be managed at the end of life. But for this, you need different recycling technologies. And it's not only for electronics. So actually, for all these major uses, we need certain recycling technologies. But in the presentation, I will just have a look for this for electronics, because there we have, let's say, the best progress over the last 10, 20 years. So at the moment, like I said, for the transport sector, we have good activities in Europe to see how to recycle partly polymers and plastic from the end of life vehicle sector. For textiles, what I said yesterday, less than 10% of all textiles are recycled. Yeah, so here in the years to come, we will need to do more recycling. And when we improve here the recycling for textiles, also we need to look to the brominated flame retardants. And for insulation in construction materials, you have seen for China, for example, that yes, these insulation foams come quite late because of the long use. In Europe, we have used these insulation materials since the 1970s. So in Europe, we have the first recycling project for EPS, XPS in the Netherlands. And the German EPA had a first project now on assessment of end-of-life plastics and polymers in respect to recycling and reuse. But you see here that, let's say, even top runners just start to think about recycling of plastic and polymers in these major use areas of brominated flame retardants and POP brominated flame retardants. So a few slides for electronics, because like I said, there we have at least now 10 years experience where different companies had full-scale projects in recycling. And therefore, when PBDEs have been listed in 2009, these companies and the countries where these facilities has been established said, oh, wait a minute, if we list the PBDEs in the Stockholm Convention, we might need to stop. So therefore, in 2009, this kind of recycling exemption were requested. But together with the listing of this recycling exemption, the BRS Secretariat and the POP Reviewing Committee asked to do a study on what is the implication of the recycling of this further allowance of the recycling of PBDEs. And actually, Alan Watson and me, we got that recycling assessment in 2010 and wrote a 350-page report on that. So you can download this from the POP Reviewing Committee document, INF documents. and working documents from POP Reviewing Committee 2010. And there we showed that there is possibility of separation and so on. In the convention, then there was a process and a guidance development, which I will show later. So therefore, when the decarbromoDiphenyl ether was listed in the Stockholm Convention in 2017, the countries did not ask for exemption for recycling. Also, when you look back on the total use, and also of the longer use of decarbromoDiphenyl ether, when you think about recycling, decarbromoDiphenyl ether is the actual driver of the problem in respect to the limits and the amounts of PBDEs in this plastic and polymers. Another reason maybe why countries at the listing of decarbromoDiphenyl ethers have not voted for recycling exemption was the experience which the research community has shown the last 15 years. These are a few studies which I would like to highlight here. One of the first studies from Chen et al. He looked to children toys in China, South China, and he found basically in all plastic children toys in China certain amounts of PBDEs and other brominated flame retardants. This is a study from Czech Republic here, coffee cup to go. You see here the black lid. Also, they screened the black lid for PBDEs, so a range of those black lids for coffee cups contain PBDEs up to 1000 ppm. This is Miriam Diamond from University Toronto. So she screened her kitchen tools and she found around 1000 ppm of PBDEs here in her salad servers. So when you make salad and the oil can then extract the PBDEs right away into your salad to make a healthy food. So what we have seen, or what the research community have shown the last 15 years, that the recycling flow of PBDEs and brominated flame retardants containing plastic was largely uncontrolled and need to that a better life cycle management and control is needed. So the global recycling sector needed a considerable improvement and best available technology, best environmental practice for separation of this kind of plastic and management of these problematic materials, especially that not these kind of plastics are not recycled in these sensitive uses like food contact materials or toys. And therefore, it is really great that we have now the PBDEs in the Stockholm Convention, and it was the right time to address these on global level. So that's the positive news. Sometimes then the industry says, yes, we have the PBDEs in this plastic, but does it really come out? This was evaluated here for kitchen tools from the group of Harrod, Stuart Harrod, Birmingham, 2017. So they used this kind of kitchen tools and did hot cooking 15 minutes with oil. And so already after 3 cookings, most of the PBDEs have been extracted from the plastic into the oil. So you see for this materials while cooking, yes, not always you put it in 15 minutes cooking oil, but normally you use it for years and years. So over time, these PBDEs will go into your food if you have such a kind of kitchen tools. Something similar was also evaluated from the Kovaci group from Antwerp. So they have analyzed toys, and also they did an assessment with saliva and showed that this kind of chemicals can come out, the flame retardants, but also phthalates can come out of these toys into the saliva of children. So there is exposure. Another good study in respect to recycling and exposure came from Heather Stapleton. So Heather Stapleton evaluated the blood of recyclers recycling polyurethane foam in the United States. And what you see here, that's a logarithmic scale of PBDEs in serum blood. You see that the workers which do the recycling have nearly 2 orders of magnitude higher concentration compared to controls, the American controls, right? And you know that Americans have already 20 to 100 times higher concentration than other people on Earth. Yeah. So there you see that the levels of these recyclers were extremely high. And also they evaluated carpet installers. So in the United States, and they found that also the levels of PBDEs in carpet installers were very high. Yeah. One reason is that polyurethane foam in the United States is mainly recycled into material which is then finally put under the carpets. So therefore, the carpet installers are handling the materials here from the polyurethane foam recycling. And another study where you see that this recycling of plastic or e-waste or materials containing these PBDEs really cause human exposure from an overview from the group of Tanabe, yeah, where they have additionally analyzed or compiled human milk levels. And what you see here are, in addition to a study from human milk from United States, Canada, and Japan, which has also specific flammability standards, that also Chinese people in the Taisho region had very high PBDE levels in human milk. And the interesting was that in another city in China, the levels were 50 times lower, Lin'an city. And the difference between these two Chinese cities was that Taishu region is one of the major regions for e-waste recycling. Yeah, so you see here that the recycling of materials containing this PBDEs with informal recycling really lead to high exposure, which was one of the questions yesterday, and where I also said that over the last 10 years in China, big improvement have happened. This kind of informal recycling also in this region has more or less been stopped and have moved to other recycling technologies. But when you look to Africa and certain other Asian countries, still this kind of informal recycling, or India, yeah, still this informal recycling is happening and people are exposed. But yes, there is an alternative, and one alternative is here, this biggest e-waste plastic recycling facility in Austria, formerly MBA Polymer, now Müller-Gutenbrunn. That's a slide from Chris Slykehouse. And he showed that in his company, when they recycled e-waste plastic, it is overall profitable from all, and a win-win from all perspective. Yeah. First, this material is growing in supply, as I showed. Yeah, we have already 10 million tons of e-waste plastic every year. It is kind of self-replenishing. It is even increasing. So when you do this kind of mechanical mining, you need less than 10% of energy compared to virgin plastic. You have less than 10% water consumption, and overall it can save between 1 to 3 tons of CO2 per ton of plastic produced. And also this company then, after the separation, about 60% of the plastic which comes in can really go back to recycling, and they sell it to even OEMs, yeah, like Philips for their new electronics. So that's a super thing. And 40% of plastics which contain the PBDEs, and also, let's say, some of other brominated flame retardants. So you not only separate the PBDEs, but also other brominated flame retardants, which might have a health issue. So they are then thermally destroyed. So in the Stockholm Convention, I mean, after the listing and the exemption, we developed PBDE but BEP guidance, including separation technologies. So for that guidance, I had a kind of lead with UNIDO. We developed it between 2010 and 2012. So when you look here to different plastics from electronics, yeah, from CRT monitors, but also to flat screens in television, and the PBDE concentration, you see that basically almost all of these categories are above the low pop content of the Basel Convention, yeah, and that this is normally considered a pop waste, yeah. Only, for example, for cooling and freezing appliances and washing machines, where the use of flame retardants is lower, because yes, they are normally do not get hot, yeah. So here they often can already meet even the low pop content of 50 milligram of per kilogram of the Basel Convention, yeah. While for other electronics, plastic from electronics, you need a kind of separation. And in the Basel, in the Stockholm Convention, but BEP guidance, we have compiled globally different technologies of full-scale plants, and also we have described the different separation techniques for e-waste plastic to separate the PBDE fractions and get at least these additives out of the plastics for recycling. And here, this is a study from France from 2018 from Henneberg et al. So he showed the levels after separation of companies for the high bromine fraction. Yeah. So after separation here, normally zinc float separation, the levels of this waste plastic come up to 8,000 milligram per kilogram. Yeah, so nearly 1% of PBDEs per kilogram. Yeah, and this can be destroyed. Yeah, in industrial countries. Yeah, unfortunately, in developing countries, we do not have destruction capacity yet. The more interesting part is here, what are the levels of the plastic where the brominated flame retardant part has been separated. Yeah, and this is a study from Sweden. And here you see from different recycling facilities in Europe, after separation for the different plastic, ABS, polystyrene, polypropylene, polyethylene, we still have in the plastic after separation of the PBDEs still a level of PBDEs above 50 milligram per kilogram. Yeah, so you cannot separate with the current technologies all the PBDEs out of the waste flow. Yeah, so some pieces, yeah, which are maybe combined with another plastic, yeah, or when you have XRT, for example, XRT separation, also you do not see all the particles and can shoot them out, yeah, then you still have PBDE finally. So if the Basel Convention would decide that 50 milligram per kilogram, which is also one suggested low pop content limit, next month to be the limit for the Basel Convention, then there will be a quite relevant risk for the overall recycling of e-waste plastic here. Good. So this is now only one limit. Yeah, and with this limit, we already see what challenge recyclers have to measure these limits. Yeah, it's quite difficult. So the recyclers, for example, say it is nearly impossible to have a detection limit of 50 ppm for e-waste plastic, especially when you consider the variation of PBDEs you have in different waste fractions. So therefore, the last 10 years, we see with the recyclers what kind of challenges they have to monitor the PBDEs in end of life, in end of life and in recycling, and to decide if a certain fraction can be recycled. But in future, more chemicals and more POPs, yeah, with these kind of limits will come into recycling. Yeah, and also we have, for example, different phthalates or cadmium, which have regulatory limits. Yeah, and also those need to be considered in the end-of-life vehicle and the management of these plastics. Yeah, I showed yesterday that the NGOs additionally highlighted that we also have brominated flame retardants in this PBDE fractions and also in some other brominated flame retardants, and that they need to be considered. So there is a huge challenge now also afterwards for setting limits. There is a huge challenge to develop the appropriate methodology, because we need robust standards like CEN standards or ISO standards for these PBDEs. And at the moment, there's only one standard, one certified standard kind of, but it's even not ISO for e-waste plastic. For other plastic from end-of-life vehicles, for example, we do not have a certified kind of standard how to sample plastics, how to analyze these plastics, that afterwards there is a certainty for the recyclers for their products at the end of life. Yeah, so this is a problem at the moment, and this problem will grow. So therefore, also from this perspective, we need to phase out and substitute these kind of hazardous additives like the POPs, yeah, where I said decaphromodiphenyl ether is still produced in the plastic to facilitate the circular economy, which we need to go to, yeah, which was yesterday highlighted, yeah, and therefore, what I said yesterday, our study here, Vanke et al. One positive news is that, yes, PBDEs have been mainly used in the 1990s. So when we look to these plastic fractions over the years, the PBDE levels are decreasing in this plastic fraction. Yeah. So here for Switzerland, between let's say 2003 and 2010, we already see a decrease of about a factor of 10 for Octa BDE, yeah, which was mainly used in Europe 1980s, 1990s, yeah, and the same decrease we will also see for the Deca BDE, yeah, but other brominated flame retardants, yeah, are now coming in, and when you look to certain alternatives, you see that they does not really look better, yeah, so that we have here really a regrettable substitution of the PBDEs by other highly brominated aromatic substances. Yeah. So the future from this perspective, from the brominated flame retardants, does not look really bright and better. And therefore, the European Chemical Agency has just published last month their regulatory strategy for flame retardants. And I would recommend all people to have a look to this strategy. I just have one additional slide as a positive end and outlook. So here, the European Chemical Agency has assessed the regulatory needs for halogenated and organophosphorus flame retardants, which is approximately 70% of the markets of organic flame retardants. So they have developed a regulatory strategy, published it in March 2023, with a particular focus on brominated flame retardants and their prioritization for restriction. So this is indicated in the roadmap, which you can download. I have put here the link to the website. And for the aromatic brominated flame retardants, a general concern has been identified here in the strategy due to their known or potential persistent bioaccumulative toxic property, or very persistent and very bioaccumulative properties. So in this strategy, they ECHA conclude, therefore, the release of these kind of flame retardants should be minimized, viewing the challenges to control releases of individual substances and the general availability of alternatives. A wide and generic restriction seems to be the most appropriate regulatory approach. Yeah. So here, the European Chemical Agency proposed a group approach to address all brominated aromatic compounds and to have a common look to them and possibly phase out all of them, or as they have proposed now also for the fluorinated PFAS, a group approach, and they are then only the essential uses to be allowed. Yeah, so this is a process which just last month started. So I invite everybody to have a look to this process. Very interesting. So for the aliphatic brominated and the organophosphorus flame retardants, the human and environmental health hazard seem more diverse. ECHA concluded compared to the aromatic brominated flame retardants, and therefore for those not this kind of a group approach is proposed. Yeah, but also this process will go for some time and is interesting to watch. Yeah, thank you for your attention. For question and answer, we wait a bit, and we will come now to the next presentation. The next presentation is a recorded presentation from Dr. Natsuko Kajiwara from National Institute of Environmental Studies in Japan. She's also a member of the International Panel on Chemical Pollution and is a member of our project to monitor the POPs in plastic project. She's doing these kind of studies now since nearly 20 years. She's working on that issue, and we have a recording, and Lisa will start the recording.
Thank you very much for your kind introductions. It is a great honor and pleasure to be here today and to discuss this important topic with you. Before I start, I'd like to thank Professor Martin Scheringer and Dr. Roland Weber and the organizer of this webinar for inviting me to speak here today. My name is Natsuko Kajiwara from National Institute for Environmental Studies, Japan. Today, I would like to introduce some of our recent findings on unintentional contamination of PBDEs in consumer products, including children's toys. This is a brief outline of my presentation today. My presentation has 3 parts. First, I would like to give a brief introduction. Next, I will touch a little bit about current situation of waste containing PBDEs in Japan. And then I'm going to look at unintentional contamination of PBDEs in consumer products. As already explained, the Stockholm Convention POPs was entering into force in 2004, initially covering 12 chemicals. Since then, the number of POPs has greatly increased at almost all the COPs. So at this moment, more than 30 POPs are listed in the conventions. Most of the newly added POPs for global elimination are plastic additives, such as BFRs and plasticizers, such as PBDEs and HBCDs, and which are added to a wide range of products. However, even though the use of PBDEs and HBCDs has been phased out, special attention should be paid to their emission potential to the environment through plastic material recycling and disposal of end-of-life products that will continue for a long time. In this slide, I'd like to explain international regulation on PBDEs. As you know very well, PBDEs have 3 different commercial mixtures, including penta-BDEs, octa-BDEs, and deca-BDEs. Their main use were different depends on mixtures as shown here. All of the main congeners in the commercial mixtures are already included in Stockholm Conventions. And low POP content, LPC, for waste is a limitation values for deciding the waste should be disposed properly, and they are decided under the Basel Conventions. For PBDEs, 3 tentative Basel LPC were proposed by parties so far. Those are 50 milligram per kilogram as a sum, or 500 milligram per kilogram as a sum, or 1,000 milligram per kilogram as a sum. But we still don't have the international agreement. So we will discuss which value is appropriate for PBD LPC on the next COP starting in next week. And also we have another important regulations in EU laws directive. And it sets maximum concentration value of total PBDs as 1,000 milligram per kilogram. So if POP's content in waste exceeded this Basel LPC, we cannot use them for material recycling anymore. Therefore, it is important to understand the actual condition of PBD contents in products, recyclates, and recycled products in each country. So what is Japanese situation? Here you can see that as there is no consumption of penta-BD and octa-BD in Japan. The use was stopped in 1990 for penta-BDs and 1999 for octa-BDs. So I think we don't need to pay special attention to the end-of-life products containing these penta or octa-BDs. On the other hand, we have been used lots of deca-BDEs in Japan, and a large part of them is for treating plastic components of electronic products. As plastic from electronics are supplied for material recycling under the recycling law in Japan, I'm going to explain a bit more in next slide. And so it is the top priority for us to know their deca-BD contents. This slide shows the outline of home appliance regulation, recycling law in Japan. Under these regulations, only the specific for home appliances, including air conditioners, TVs, and refrigerators and freezers, and washing machine, clothes dryers, are the target of recycling. We have achieved the target rates for material recycling as shown here. And among these products, TV casing are the main components treated with deca-BD until RoHS directive started. This is a common recycling process of TV casing in Japan. CRT and flat panel TVs casing are separated into materials by manual dismantling and then mechanical shredding. Some of them are sold or exported without shredding, just as mixed plastic, like scrap. And this slide shows the international circulation of end-of-life products containing PBDs. Most of the replastic collected in the recycling facilities in Japan are not always consumed in Japan, but instead exported to other Asian countries. It also means that recycled products using e-waste is probably imported back to Japan. Therefore, we conducted a survey to understand the current status of international circulations of PBDs containing waste plastic. This slide shows the outline of the samples we used in this study. To understand more about unintentional contamination of plastic recycling stream by restricted PBDs, we collected a wide range of small plastic items, total of 540 items, and after dismantling, it is like more than 1,000 components, including children's toys purchased in Japan, and also 17 other countries between 2015 and 2019. We have 3 categories, including giveaway toys and 100-yen shop products, and also cheap plastic products purchased overseas. This is the breakdown of the origin of the products we got from other countries. So like 64 samples from India and 47 from Belgium. And so we have totally from 18 countries. This is the picture of the giveaway toys. And it is very common in Japan to offer giveaway toys to children, for example, at the restaurant or in the airplane or at the post office and so on. This is the example of 100-yen shop products. We have like water gun, a calculator, and those toys. And this is the example of plastic products purchased overseas, like clothes hangers, water pipes. This is a hair accessories and some toys for kids. This slide shows sample preparation and chemical analysis. All the samples collected for this survey were dismantled manually to each component, and each component, the bromine contents were screened by this handheld XRF instrument. And the samples with bromine contents, more than 30 milligrams per kilogram, we select those samples and we pulverize those samples and ultrasonically extracted and finally analyzed by GC-MS-MS. From next slide, I'd like to show you some results and some discussions. This slide shows the bromine content, plastic components, totally 1,139 components. So in this pie chart, the darker blue color means the higher the bromine contents. And hand-to-hand XRF analysis revealed that 219 samples, components, that mean like about 20% of the total samples contained bromine at the concentrations of more than 30 milligrams per kilogram. So those samples we use for chemical analysis of PBDEs. And the chemical analysis of these bromine positive components revealed that 109 pieces, that means 10% of the total, mainly those made of black colored plastic, contain PBDEs at concentrations ranging between 35 to 10,000 milligrams per kilogram, as shown in this figure. And the maximum contribution was from BDEs. In this slide, the red bar indicates from the toys and blue bar indicates from the data from other items. And these PBD concentrations were not enough to impart flame retardancy, suggesting that the recycled plastic used to manufacture these consumer products probably originated from electronic waste like CLTTV casing. I would like to show some samples containing PBDEs. This is a toy guitar containing about 10,000 milligrams per kilogram PBDEs. And this is a toy car, and the bottom part of the car, this black plastic, contains 200 milligrams per kilogram of PBDEs. And the toy gun also contains quite high concentration PBDEs, like 3,000 milligrams per kilogram. And this is a bit interesting example for me. Like this is the accessory bees toys, and the bees covered by silver painting. But when I scratched the surface, the inside was black plastics, and the plastic contained about 4,000 milligrams per kilogram of PBDEs. This is the example of the PBDEs found in other items. This is the clothes hangers containing about 1% of PBDEs. This is the highest concentration we found in this survey. And this is the flashlight containing like 0.5% of PBDEs. And this is the water pipe. I think this is from African countries and contains about 400 milligrams per kilogram of PBDEs. So, and this is a calculator containing about 2,000 milligrams per kilogram PBDEs, and also those kind of black hair accessories containing about 500 milligrams per kilogram PBDEs. So this survey demonstrated that plastics containing DECA-BDEs end up in products where they serve no functional purpose. To contribute to the circular economy, the recycling plastic waste should be promoted. But however, urgent action is needed to prevent plastic additives of concern, including PBDEs, from entering new products used in daily life, particularly those used by children. To achieve this, it is necessary to determine POP-containing products in each region and possibly at each recycling facility. Then, what we can do now? In my personal opinion, if we really want to reduce the concentration of DECA-BDE in circulating resources, we need to take early action as soon as possible in each country to prevent CLTTV stocks from entering the recycling stream. To do so, I mean, a step closer to the POP-free environment, we need more communication with policy makers and recycling industries. And also we need to support for capacity building of POP analysis in circulating resources in developing countries. Finally, I would like to express my special thanks to all those indicated here who work with us on this project. I would like to thank Japanese EMPA for funding our research, and also thank you very much for your kind attention. And thank you very much for taking the time to join today. Thank you very much. That's all from my side. Thank you.
About understanding short chain and medium chain chlorinated paraffins in plastic and some lessons learned from PCB in plastic. As shown, 2017, the short chain chlorinated paraffins were listed in the Stockholm Convention, and currently the medium chain chlorinated paraffin are assessed in the POP reviewing committee. They are already here in Annex F, the risk management evaluation, and might be listed in 2 more years. When we look to the history of chlorinated paraffins, we see that they have been regulated in some countries since the early 1990s and have been proposed in 2006 to be listed in the Stockholm Convention by Switzerland, but it took then 10 years to get the short chain chlorinated paraffins through the POP reviewing committee. And then in 2017, the short chain paraffins were then listed. One issue to highlight is that China and India have not yet ratified short chain chlorinated paraffins yet. And because, as you will see, they are the major producer, this is a relatively high uncertainty. When you look to chlorinated paraffins, it needs to be stressed that it's a very complex mixture, analytical challenges, which we will show in further webinars. So we have 3 different chlorinated paraffins defined. The short chain chlorinated paraffins with a carbon chain length of 10 to 13, the medium chain chlorinated paraffin with a chain length of 14, carbon chain lengths of 14 to 17, and the long chain which have chain lengths longer than 18. The chlorination content in chlorinated paraffin depend on the production and the product. So normally it is somewhere between 30% chlorine and 70% chlorine. And due to the variation in chain lengths and chlorination degree, we have around 200 commercial chlorinated paraffin mixtures in use. The Stockholm Convention have listed short chain chlorinated paraffins with a chlorine content greater than 48% as POP. But also other chlorinated paraffin mixtures with more than 1% of short chain chlorinated paraffins are considered POPs. For the medium chain chlorinated paraffins currently in the POP reviewing committee, it is proposed that those which have a chlorine content more than 45% are proposed in POP. They meet the Annex D criteria and are currently assessed for Annex F. When the short chain paraffins were listed in the Stockholm Convention, a wide range of exemptions were asked, especially from developing countries. So these exemptions have been granted, and just a year ago, the first country have registered here for exemption. That was Vietnam, which found that about 15,000 tons per year is used in Vietnam. The exemptions which have been granted in the Stockholm Convention was for flexible PVC as secondary plasticizer, except for toys and children products, then for rubber transmission belts, for leather, fat liquoring, for lubricant additives, waterproof and fire retardant paints, for adhesives, which includes, for example, polyurethane spray foam, and for metal processing. So therefore, short chain paraffin are further produced, used, and released. When we look into the environment, we see what kind of strong increase of pollution levels we have in the world. So this is also logarithmic scale study of purpose in the Chinese Sea, where over more than a decade, 10 times increase was observed in levels. Also, for polar bears, you see that not only the short-chain chlorinated paraffins are found in the polar bears, but also medium-chain chlorinated paraffin were found in the polar bears. And when you look to the polar bears analyzed 2015-16 compared to 2003, we have a very strong increase in particular of the medium-chain chlorinated paraffins. Yeah, so overall medium-chain chlorinated paraffin production and release is higher than short-chain chlorinated paraffins. And in China, in the study of some biota, they found, when you look here, this is the total POP content in these three animals. The short-chain chlorinated paraffin make more than 90% of all POPs found in this biota here in the Yangtze River Delta. We see this increase in Europe for the chlorinated paraffins since the 1950s. Yeah, here this is a sediment core from Lake Thun in Switzerland. What is interesting is, yes, we see for the PCBs already a decrease in the 1970s. And while the PCBs were decreasing, the chlorinated paraffin substituted the PCBs in this open application and were increasing. When you look to the levels, here the peak level of PCB in sediments is around 17 nanogram. Here for the chlorinated paraffins, already in 2010, the level in Switzerland were 16 nanogram per gram. So yes, one POP substituted by another POP, bioaccumulating, higher production rate, higher concentration in the environment. Interesting here for PCBs in this figure is that you see a strong decrease of PCB levels in the sediments in Switzerland after 1970s. Yeah, so this also shows what the stop of PCB use in open applications in 1972 had a huge impact. Yeah, at the moment, Stockholm Convention managed the closed application, which of course is important for the waste oils, but the open applications in respect to the release to the environment, yeah, is overall more relevant. Yeah, I showed today already, when we look into the human milk study, chlorinated paraffin have the second highest POP concentration in human milk, only topped by DDT, because some countries have a huge DDT concentration, especially in Africa and some Asian countries. It needs to be stressed that the short-chain paraffins have lower toxicity compared to PCBs. So here EFSA evaluated the data and concluded that the margin of exposure is 3 to 5 times 1,000. So EFSA, but also stressed that there is a lack of toxicity for developing a tolerable daily intake. Yeah. So today, sensitive endpoints for chlorinated paraffins like immunotoxicity, neurotoxicity, developmental toxicity of children are not really assessed enough. And when we look back to the 40, 50 years research for PCBs toxicity, we see that after decades, these kind of data only come out. We see that the human milk in particular developing countries are quite high. The highest short-chain chlorinated paraffin concentration is found here in Africa, 610 nanogram per kilogram lipid, higher than Asian countries or the KRULAC region. Short-chain paraffin, yes, they meet the POP properties. They are carcinogenic to rats and mice. They are categorized as group 2B carcinogens, as possible carcinogenic for humans. They have reproductive toxicity to mammals and birds. They have effects on the thyroid hormone system, toxic to aquatic organisms, and they are neurodevelopmental toxicity for zebrafish. So the current, let's say, levels where the tolerable daily intake from the data, what we have as most sensitive endpoint, which would be milligram per kilogram per day, is unfortunately only based on this toxicity data, and this needs strong improvement. When we look to the life cycle of chlorinated paraffins, it is basically the same like I showed for PBDEs. So we have for sure a large exposure from the products, and in future also from recycled products. at the moment now countries start to look into their chlorinated paraffin use. And we have done some pilot countries and found it very difficult because it is challenging, especially to find the chlorinated paraffins which have been added to products, especially here in China and in India. So this is a study from China about the total production. So we have since 2010 more than 1 million tons of chlorinated paraffins produced. The current production is estimated to around 1.4 million tons. The total production of short-chain chlorinated paraffins is estimated to today 400,000 tons, but often it is in chlorinated paraffin mixtures. So therefore, in our estimate, the total amount of chlorinated paraffins containing short-chain chlorinated paraffins above 1% is likely rather 900,000 tons a year. Yeah, the largest producers are China and India. For China, of chlorinated paraffins, for China, we have an estimate of around 700,000 tons per year. In Chen et al., I think it could also be higher, considering how they calculated it. Details we can discuss another time. And they estimate that the chlorinated paraffin production in India also have reached 375,000, but it's also rather from their modeling. Yeah. So for India, we do not really know the details, but India is doing at the moment their NIP update. And so I hope that we get more information from there. We have also production of chlorinated paraffin in other countries like Bangladesh, Egypt, Qatar, Russia, South Africa, United States, and some others. Yeah. Major use then for the inventory and for the assessment is additives in PVC production, rubber production, adhesives, leather production in textiles. And the best study which is out there at the moment is this study for China, which have assessed 124 products. Yeah, PVC, rubber, polyurethane foam, but also they have looked into paints. And what they found is really that 70% or more than 70% of short-chain chlorinated paraffins and medium-chain chlorinated paraffins directly go into the PVC production. Yeah, another more than 10% go into rubber production and also into polyurethane foam production. And because China produces more than 50% in the world, these kind of products are a main driver of the total use of PVC and in future the management of PVC. Yeah, and you see here, therefore, for China, we have more than 80% of use of chlorinated paraffins directly in plastic and polymers. For other countries, unfortunately, data are only available from 20 years ago. Yeah, where, for example, for Europe, yes, there was also at that time high use for metal metal lubricants and other lubricants. We do not have real new data. So with the Stockholm Convention implementation, this will change. And until then, we can only really use this review article from Chen et al. Yeah, with their estimate, which is mainly based from China. Yeah. And they concluded from this data that also for the world, let's say more than 50% overall is used in PVC, that there is still more than 10% in metalworking fluid, more than 10% in rubber, and then in this kind of adhesive sealants like the polyurethane foam. But here, I would say the study is a bit guessing because we really don't know, for example, for what purpose India is using their more than 300,000 tons of chlorinated paraffins. Yeah, so here more assessment is needed. What we know, yes, also for Europe, we have still use, for example, in polyurethane foam. I showed yesterday high levels up to 50% in this polyurethane foam, but for Europe, this is already, the short-chain chlorinated paraffins are already regulated. So here we find 50% of medium-chain chlorinated paraffins. Another impressive study on chlorinated paraffin use comes from Professor Vetter from Hohenheim University. He has he has analyzed baking ovens in Germany, and he found that in 50% of German baking ovens, the levels of medium chain chlorinated paraffins was very high, up to the percent range of the fat inside sampled of the baking oven. Yeah, and this comes from cables and plastic in the ovens and are directly transferred out of the plastic then to the food. This was just published last year. The release then from the baking oven to the food. Another important study and interesting study is the food blenders. So Stockholm University have found that food blenders partly contaminated their fish samples. And then they started to analyze food blenders. And then they found that 8 of the 12 food blenders contain chlorinated paraffins and were releasing these paraffins into the food. And repeated use here did not lead to a reduction of the release. Yeah, so here they were partly as lubricant or in the plastic parts, and from there directly go into food and into human exposure. Interesting was here when they looked into the distribution of short and medium chain chlorinated paraffin, that it was always a mixture. So in these mixtures, we just find, for example, in China, Xia et al. Published in 2021, that in average, these chlorinated paraffin mix CP 52% chlorine contain in average around 30% short chain chlorinated paraffin. And the same was found in this study from this year from Weng et al. In plastic curtains, where he assessed the release of these plastic curtains into the indoor environment and concluded that there is considerable health risk through inhalation or thermal contact to this. So let's say these data from China are only one of the few hardcore data. In most developing countries, we do not have data, but we need to do this kind of inventory now to think about management of developing countries. And therefore, over the last 4 years, I had different projects with the Stockholm, Basel, Rotterdam, Stockholm Secretariat to do initial inventory of short chain chlorinated paraffins, and I also looked to the medium chain chlorinated paraffins. So we have therefore developed a methodology to do a preliminary inventory with the use of especially import data of these kind of products like PVC and rubber containing additives. Yeah. Additionally, for the studies here in Brazil and the study in Indonesia, we also checked the industry. So yes, for Brazil, we found also imports of chlorinated paraffins, and we could track some of the uses. Yeah, but let's say the largest assessment we finally did from this UN Comtrade database for PVC, rubber, and plasticizer. And this we also did then in Nigeria, together with Professor Babayemi, University of Medical Science of Ondo, and Professor Innocent Norom from Abia State University. And here we did a detailed assessment of the import. And the first thing what is quite good and what can be done from the country is to look to the different HS codes from the UN Comtrade database, because the different type of PVC containing softeners have different HS codes, and also HS codes of PVC which does not contain plasticizer. So based on this, we did an assessment here for Nigeria. And the first thing what you see here, when we look into the total import of plasticized PVC to Nigeria between 1996, so also there it's good you have data from the last 20 years to 2018, is that we see that overall we are in the 100,000s of tons of imported plasticized PVC. Yeah, so overall Nigeria has imported more than 1 million tons of plasticized PVC over the years. And what was interesting is that we saw that also PVC waste has been imported, more than around 150,000 tons, yeah, the last 20 years to Nigeria. Also, we have done the same assessment for rubber and rubber products. And also there, yeah, in rubber products, the chlorinated paraffin content can be in the percent range, and that was, let's say, the second highest use, what we found in China. And also here, for rubber, the HS codes are differentiated in rubber, which contained additives or let's say raw rubber. So also here we have done an assessment of plasticized rubber for Nigeria, and have found that also the amount of these is going to the million ton scale when we look back the last 25 years. So then we used the data from China, from the additives in PVC and the additives in rubber and the additives in the polyurethane foam for the imports from China to Nigeria, yeah, of these products, PVC, rubber, and polyurethane foam. And when you take this and calculate it, then you come to the conclusion that around 37,000 tons of short-chain chlorinated paraffins have been imported in these products to Nigeria over the last 25 years, with by far the highest concentration here in PVC. Also for medium-chain chlorinated paraffins, where the data are available from the Chinese study, we have estimated that the levels are higher, so 60,000 tons of medium-chain chlorinated paraffins have been imported, 50% in PVC and 50% in rubber. So the Chinese studies have found that higher levels of medium-chain paraffin mixtures are used in rubber. And when we compare this amount of total chlorinated paraffin with the total global production, we are in the right range of order of magnitude. So even if you just would take the population of Nigeria and calculate it, you would even come to a higher import overall of chlorinated paraffins, considering the per capita. So in Europe now we have already monitoring in consumer products with this RAPEX system, where different EU states have done screening studies. And there we see that we have chlorinated paraffins above 1,500 milligram per kilogram, short-chain chlorinated paraffin per kilogram, above the regulatory limits in sports equipment, in children toys, here the red ones, pistol, bath toys, game controller, plastic doll, and then in a range of cables. Yeah, so basically PVC, rubber, and some other polymers. We will have more details in the presentation of Yago Guida after me. So this review of Chen et al. Did a total estimate of the total amount of chlorinated paraffins produced in history. So it was estimated that in total 33 million tons of chlorinated paraffins have been produced, and 13 million tons are still in use. They have estimated, and they have done also here differentiation between short, medium, and long chain chlorinated paraffins. You can look at the details. And they have also estimated in what kind of products we still have these 13 million tons. So yes, the main is in PVC, then a bit in rubber, and the other is polyurethane foam and other sealants. So when you consider here these 13 million tons, we have likely 20 to 100 times higher concentration as a product, because we have around 10%, or sometimes for rubber it's lower than 10% in the products. Yeah, so we are talking here about 100,000 tons of products, around 200 million tons impacted PVC and rubber and polyurethane products. Yeah, and every year we have more than 1 million tons of chlorinated paraffins containing SCCP and MCCP still, which is going further in PVC and polyurethane foam. So every year, this means we have more 10 million tons of POP-containing polymers newly produced and going into production. The entire product categories of plasticized PVC might exceed the Basel Convention low POP content, which at the moment is also discussed, 100 milligram or 10,000 milligram. And it might go and reach the billion-ton scale over the year. Yeah. So here we are at a dimension which is absolutely challenging. I mean, for recycling, but also when we think about destruction. Yeah, it is highly chlorine containing. So the management the next decades will be really challenging for all countries. Additionally, a range of other additives in PVC like DHP, cadmium, and lead we have where we need to manage these materials. Yeah, and yes, we have to move to a circular economy. I closed the cycle. I started with it yesterday, and we need to look here to chlorinated paraffins, to the PBDEs, and we need to manage them. Yeah. For chlorinated paraffins, we see that in future, the recycling cycles of flexible PVC are impacted, of rubber recycling, but also construction and demolition waste containing these kind of materials, PVC, but also we have other recycling cycles like oil recycling or leather recycling, which are relevant. So we have huge future recycling problems ahead for chlorinated paraffins, like for the PBDEs. And only 2 slides for the PCBs. We saw in Germany for PCBs and other industrial countries that we have challenges also for cable recycling. So we set a limit of 50 ppm. We set a limit in Germany for construction and demolition waste of 1 ppm. But the monitoring of it is challenging and is expensive. Yeah, also for others. So therefore, yes, we need to phase out, yeah, because when we will have to set limits, yeah, and these limits will challenge and will make recycling more expensive, yeah, but this will come. And just learning from the PCBs for chlorinated paraffins. At the moment, chlorinated paraffins are considered that the levels what we have as a daily exposure is still okay, yeah, but the same was said for PCBs in the 1970s and 1980s. And then come the health assessments. And the tolerable daily intake for PCBs were decreasing. And I nearly can promise you that something similar might happen to the chlorinated paraffins. Yeah. So I showed yesterday that the TDI, the tolerable daily intake for PCBs since 2003 are so low that actually the people which are in buildings with PCBs are above that tolerable daily intake, and that in Germany, sometimes for the decision, if there will be a renovation, kindergarten and schools sometimes are broken down. And only in 2015, the International Agency for Research on Cancer put PCB into the category 1. Yeah. So you see, it takes really decades that you finally get out the right toxicity. And this picture I showed you, yes, this is me at my university in 2017, and that's Dr. Warbelo. Dr. Warbelo was one of the most experienced person for remediation of large contaminated sites. So his wife was a teacher, and she died out of cancer. Yeah, and for him, he was sure. So she was in a PCB school working there for 20 years. Yeah, and I showed you at the moment there are these court cases in America of cancer of teachers. Yeah, and unfortunately 3 years ago also Dr. Warbelo died out of cancer. Yeah, so he dealt with PCB and PCB management over a long time. Yeah, so therefore I want to highlight that we need a very thorough and a more fast assessment of these chemicals, and especially high volume chemicals like chlorinated paraffins. Yeah, we need to have these data that they can be appropriately regulated. And So this is one wish to the audience, that if there are toxicologists, that you do more studies in toxicity assessment of the chlorinated paraffins. Yeah, thank you. Now we come to the large presentation, the last presentation before the break. And sorry that we are close to the break, but the second part, the presentations will be a bit shorter. I think we can make the time. So the next speaker will be Dr. Yago Guida from the National Institute of Environmental Studies in Japan. So he's also a member of IPCP. Dr. Guida is at the moment a postdoc in the Material Cycle Division of National Institute of Environmental Science in the group of Dr. Kajiwara. He's currently analyzing the plastic pellet samples for our UNEP IPCP CHEF project. He's originally from Brazil, from University of Rio de Janeiro, and supported the Brazilian Environmental Ministry with the update of the Stockholm Convention implementation plan. And his presentation will be monitoring of chlorinated paraffins in plastic products. So over to you, Yago. You need to unmute your microphone. We can see your presentation, but you need to unmute your microphone.
Okay.
Yeah, super.
You hear me?
Good.
Okay. Thank you very much.
Perfect. Welcome.
Thank you very much, Roland, for the nice presentation. Thank you, everyone, for coming here to listen to our presentations today, to support our project. So, as Roland just said, my name is Yago Guida. I'm originally from Brazil, but I'm currently working in Japan, and where I have developed some studies on chlorinated paraffins, and I'm still working on that and trying to expand our knowledge on chlorinated paraffins in polymer products, and also in some recycling streams. That's my current topic at the moment. So I'd like to present some studies, not just our studies, a compilation of some important studies to understand the fate of chlorinated paraffins in products. And to begin with, it's important to highlight some of the things that Roland has already mentioned, but I will pass very quickly for that. So, for example, important to mention that the chlorinated paraffins, they can have a variation of chlorine numbers and carbon numbers in their chain length, which makes them feasible for multi-purpose applications. So they have been used for several applications, from metalworking fluids, lubricants, painting, sealants, flame retardants, and also plasticizers. And in the academic literature, they are generally divided as short-chain chlorinated paraffins, medium-chain chlorinated paraffins, and long-chain chlorinated paraffins, according to the chain length of according to the carbon chain length. And one important thing to have in mind is, for example, the total amount of chlorinated paraffins that Roland just mentioned with us, that approximately 30 million metric tons of CPs have been produced, and almost 40% of each, which still reside in used products by 2020. And here I would like to highlight that the biggest share, the largest share of chlorinated paraffins are used in PVC and then metalworking fluids, but I would say also some lubricants are considered metalworking fluids here, but they can work as lubricants for other purposes as well, like polymer production. And we are going to talk a little bit more about that later. So the global cumulative emission of CPs have increased throughout the last years. And while the production, use, and emission of CPs started declining in some regions of the globe, like the Western Europe and US, they remain high in China, which is the largest global producer of CP. And in 2017, we had the restriction of SCCPs under the Stockholm Convention that were listed under Annex A for elimination. Recently, in 2021, MCCPs were also proposed for listing as POPs and were recommended to be added to the European Union HOS directive. And SCCPs are also currently listed under the Basel and Rotterdam Conventions. And under the Basel Convention, we have two tentative low POP content limits of 110,000 milligrams per kilo. And implement those conventions, there are some activities that the country parts must perform, and some of them are quite challenging regarding the complete implementation for chlorinated paraffins, the now SSPs, but probably in the future also MCSPs. So those country parts, signatories of the Stockholm Convention, they have to develop POP inventories to define proper chemical management within the country context. They have to assure that SSPs are only used for the specific exemptions defined in the leasing decision, and also that they have to apply for those use, and that if other CPs that are traded might be traded as MCSPs or LCSPs, if they contain more than 1% SSPs, they should also be considered POPs. So, and finally, it's important to promote environmentally sound management of end-of-life products containing SSPs and SSP waste, which is also one main task under the Basel Convention. And the main challenge for that are that CPs are produced and traded based on the chlorine content and not on the carbon chain length. So several studies have reported that commercial CP mixtures, they contain more than 1% SCPs, even though they are not listed as SCPs. And also some products, technical mixtures that are listed as MCSPs or LCSPs, they contain more than 50% SCP sometimes. And other important thing is that China is the largest global producer of CPs with a production of approximately 1.5 million tons. And China is a very relevant commercial partner of many countries, which means that the products that are being additivated with chlorinated paraffins, they might be exported to several countries worldwide. And most of the Chinese CP production is used in PVC manufacturing. So for SSPs, it was estimated almost around 90%, and for MCSPs, 75%. And another challenge is that products containing CPs are not labeled, and both commercial CP mixtures and products containing CPs do not contain specific codes to track their foreign trade data. So we have to do these kind of estimations that Roland just showed to us, which is a little bit tricky, but it's what we have for now. So back in 2020, we have published this study to support the implementation of the Stockholm Convention when we tried to understand the chlorinated paraffins fate in the technosphere, the contamination through chlorinated paraffin production, and also in products. So one thing important to highlight from this study is that in this review, we compiled several studies that have measured SSPs, MCSPs, or LCSPs in products. And the highest concentrations of SSPs, they were measured in toys, which is very concerning regard children exposure, and also PVC, that was expected because it's the main use. But also for rubber, they can have very high contents, like up to the percentage in the concentration. And it's also worth mentioning that CPs, they have been measured, although in lower concentrations, but they also were measured in food packaging, and also different kind of polymers like PE and PP. This is probably because they can be used as lubricants during the processing of plastic manufacturing, and or if products are recycled from feedstocks treated with CPs. So there is one recent study that investigated the occurrence of chlorinated paraffins in consumer products found indoors. So 27 indoor products were analyzed for CPs, though those products, they were purchased in Canada. These studies from Canada, they were purchased in 2019, and some of them after 2013. And it's worth mentioning that CPs are restricted in Canada since 2013. So here, this study, they didn't not evaluate the polymer types, but it's interesting to show that some products that we have daily contact, they can have high contents of chlorinated paraffins, and also that some of them, the major contribution is still for short-chain chlorinated paraffins, even after its restriction. So this is the other study that Roland mentioned with us, that where the Chinese group, they have identified the main uses of CPs in China, and most of it was in PVC, followed by rubber and adhesives. And here another study from some colleagues that are also involved in these projects with us from Thailand, where they have screened the presence of some plasticizers in several products made of PVC. And here we can see that CPs, they are quite frequently detected in those products, like in boots, in cables, in hoods, and also floorings. So some other plasticizers as phytate and CPs, they were quite frequently found in those products. Following this body of evidence, we conducted this study here in Japan regarding short and medium chain chlorinated paraffins in polyvinyl chloride consumer goods that are currently available in the Japanese market. So understanding the huge amounts of chlorinated paraffins and their main use, we tried to assess SCCPs and MCCPs in contents in PVC consumer goods available in the Japanese market. And chlorinated paraffins, the SCCPs, they are restricted in Japan since before this Stockholm Convention restriction. So briefly, what we did was we purchased some products from 2017 to 2019 in 100 yen store. That's like $1 store. And we screened those products by XRF to check the chlorine content and identify PVC products. So we might have some presentations on methods in the next part of this webinar series. But briefly, the samples were cut, then powdered into a thin powder, extracted in ultrasound bath with organic solvent, then a simple step of cleanup with acidified silica gel, and then it was the CP contents were measured by LC-MS. So in summary, we found CPs in 42 out of 87 samples. So here we have the concentrations range and the median concentrations for SCCPs in cable sheets, in house interior products, and in children's products. So we found the highest concentrations in children products and the frequency of detection for SCCPs, and here for MCCPs. So for MCCPs, the highest concentrations, they were measured in cable sheets. And most of the PVC consumer goods purchased in Japan, they were manufactured in China. However, all products not made in China, they had a total CP content below 0.1%, which means that that huge production of CPs in China and then the application in PVC products is reaching other countries and even countries where CPs are regulated. And the highest concentrations were detected in children products. But besides the most contaminated sample, that was a children's flip-flop, only 3 other samples had SCCPs above 1%. And it's interesting because the intentional application of CPs in PVC, a secondary plasticizer, it goes from 7 to up to 20% of the weight of the product. So it could be, in this case, it was 12% for that flip-flop that I mentioned. In total, 15% considering both SCCPs and MCCPs, but it might be that those products were also contaminated unintentionally. So in total, we had 11 products with CP contents above 1%. So therefore, intentional CP application as plasticizer or flame retardant cannot be assumed for most of the products, as I just mentioned. The children's products were more impacted by SCCPs, whereas cable sheets and house interior products were more affected by MCCPs. And the SCCP-MCCP ratios show that although it's possible to have single chain length groups, several products are still impacted by CPs containing more than 1% SCCPs. As I mentioned in the introduction, technical mixtures, CP technical mixtures containing more than 1% SCCPs, they should be treated as POPs. And here we can see, for example, in green, the SCP contribution for some of the products. For some cable sheets, it's reached 100%. In house interior products, it was interesting that we only saw MCCPs, but for children products, most of them, they were more impacted by SCCPs, but we can still see that CPs, they are used as mixtures and not as individual chain length groups. So comparing our results with some of the previous studies, we had, for example, that regarding cable sheets, those that we have measured here in Japan, the SCP concentrations, they were higher than those from Belgium, but considerably lower than those from China for SCCPs, and also for MCCPs was the same. For house interior products, those purchased in Japan, they had no SCP contents, but some MCCP contents, but those contents were considerably lower than those from samples purchased in China that have reached up to almost 20% of in the medium concentration of, for example, soft plastic curtains. And regarding children products, up to then, the period we have published this study, there was only one report from IPCP that they have also measured SCCPs in different children's products and toys from different countries. We saw that our highest concentration, it was much higher than those they found, but the median concentration, it was below. And that study, unfortunately, they have only measured SCCPs, so we could not compare the concentration for MCCPs. One thing that's important to highlight here regarding the difference between MCCPs and LCCPs in different categories of products is that we could speculate that the children toys, they have more SCCPs probably because they need to be cheaper than the other products. And it has been reported that chlorinated paraffins, they are cheaper than plasticizer like phthalates. So they are used to make the production cheaper. But in this case, it might be impacted those that are more vulnerable to the contamination by CPs. And regarding the Basel content, the low pop content limits established by the Basel Convention, we found that for samples, they were above the highest LPC of 10,000 milligrams per kilo. And if the lowest Basel low pop content limit is adopted for SCPs, then we would have at least 14 samples that were above 100 milligrams per kilo of SCCPs. And this is very important because once these limits are defined and we choose one limit, if it's the lowest one, it will increase considerably the amount of waste containing CPs that needs to be destroyed and could not be recycled. Oh, sorry. So in summary, we can say that SCCPs are still often present in PVC consumer goods currently available in the Japanese market, despite the restrictions in Japan, that some manufacturers may use technical CP mixtures in PVC products with less than 1% SCCP content, but many other products still contain larger fractions of SCCPs. In most cases, CP contents were below the contents report for intentional use in PVC manufacturing, which suggests a contamination and not intentional use for most of the projects or the products. And potential intentional SCP application was found in children's products, for example, for that flip-flop, where we found 15% of the weight is CPs. And CPs were predominant in products made in China, highlighting the need to establish a wide monitoring of imported PVC products. And considering the low pop content limits proposed under the Basel Convention, waste and recycling streams also need to be monitored for the proper implementation of the Stockholm Convention, the Basel Convention. Those are some of the references I have used for this presentation. And here I leave you with a nice picture from Japan. Thank you very much for your attention. That's it.
Thank you very much, Yago, for your very informative presentation. Now we have a question and answer session, and yes, some questions already came in. one question to me is, could you please give more explanation on how aliphatic brominated flame retardants and organophosphorus flame retardants seems to cause more hazard than aromatic ones? No, I didn't say that. And also the European Chemical Agency does not say that. So they highlighted, the European Chemical Agency highlighted that the aromatic brominated flame retardants are of this specific concern. Yeah, and that they will now first have a detailed look to this group of brominated aromatic flame retardants. And they said then the other group, organophosphorus flame retardants and aromatic, the aliphatic brominated flame retardants, there might be of different concern or lower concern. So there they need to have a closer look than later. Yeah. So the first regulatory activity of the European Chemical Agency is targeting aromatic brominated flame retardants. Yeah, but I have shown yesterday that for organophosphorus flame retardants there are health concerns. Yeah, so there are studies on their toxicities, and also we have seen yesterday that they seems to impact the sperm quality and have other endocrine disrupting activities. So therefore, of course, also to the organophosphorus flame retardants, regulatory actions might be needed. And for example, California EPA has categorized one of the chlorinated phosphorus flame retardant as carcinogenic. Yeah. So, but yes, let's say this is then the second base. Then a question from Yuyun Ismawati. So she asked if for the Nigeria study, for the UN Comtrade database, if Professor Babayemi have also cross-checked the data recorded by the Nigerian import and export statistics. The UN Comtrade database is based on the reporting from countries. So this means the Nigerian government is reporting to the UN Comtrade database their data. Yeah, some countries are not reporting. Yeah, so that's voluntary. So therefore, the UN Comtrade database and the Nigerian data are likely the same. And we have also checked for export. Yeah, so we have looked if plasticized PVC or plasticized rubber is exported. So that was minor. So therefore, the import is the driver. Another question, also from Mrs. Yuyun Isbamati, is that her group found polyfluorinated hexane sulfonate in rubber gram samples, but you have not analyzed them for short-chain chlorinated paraffins due to the funding. What will be the practical approach to conduct a study in developing countries on POP in products so it will result in an effective report and produce sound recommendations? I mean, that was, I think, also one reason why UNEP was interested in these POPs in plastic. Yeah, to generate more data on POPs in plastic from developing countries, from the different regions. Also in 2010, we had a small-scale funding from the BRS Secretariat to monitor PBDEs in plastic in Nigeria. So that's one approach. There are many research groups worldwide, and I think it's great what IPEN is doing. And maybe this kind of cooperation, let's say from organizations which have the link to developing countries and laboratories in industrial countries with analytical capacity, yeah, like we do in our project. So this could be also one way forward to get more data. And of course, the development of capacity in developing countries is important. And this links to another question which came to Dr. Natsuko Kajiwara. So here, the question is, could any of the speakers today share some ideas of what kind of capacity building and will be reasonable and realistic to promote in developing countries? I mean, one thing could be really this kind of tandem cooperations. What happens at the moment, for example, Dr. Guida from Brazil is at the Japanese laboratory, but I know that UNEP is at the moment developing the next global monitoring plan for POPs. And one considerations for this upcoming project is also that the capacity building of laboratories in developing countries should have a priority in the next global monitoring plan. Then one question, what is your recommendation for the most appropriate approach to deal with chemicals, including POPs, that already contaminated the plastic value chain for this upcoming agreement, plastic treaty? It seems that chemical banning policy does not fit with chemicals that have already been contaminated. And I think also here, then that plastic treaty could possibly learn from the Stockholm Convention and our activities we are currently or which are currently conducted under the Stockholm Convention with the management of PBDE containing material flows. Yeah, and what I showed yesterday, those projects in Nigeria, Ivory Coast, China, and China, so they are ongoing. And for sure, for the plastic treaty, which will be, let's say, hopefully agreed 2024, yeah, there will be more results until then. And I think that this kind of lessons learned from projects from monitoring POP in plastic should then also be applied for other legacy chemicals in plastic. I mean, I highlighted for PVC also this DHP, the phthalates. Then the question, what would be best approach to destroy the plastic streams that cannot be recycled due to the high content of chlorinated and brominated POPs? I mean, at the moment, yes, I mean, incineration is at the moment the largest capacity. I said that, I mean, when you look to developing countries, often you do not have BAT, or no, you normally don't have BAT incinerators in developing countries. So normally at the moment, incinerators in developing countries does not work. And Yuyun showed yesterday on the pollution. Cement industry is an option. Yeah, cement industry, cement plants are in many developing countries, have a capacity, have destruction capacity, but we have this halogen challenge in cement kilns. So cement kilns can only accept to a certain amount of chlorine and bromine, so which can be calculated. There is an additional technical feature, which is the so-called chlorine bypass, which should also work for bromine. So this can be implemented in cement kilns, but let's say the cost is relatively high. So this could be, let's say, one part of the way forward. And also here in our project with China, we have incineration and we have the cement kiln pilot project for the destruction of HBCD containing plastic. Good. Is there another? Yes. One question to Dr. Yago Guida. I would like to ask how short-chain paraffins use can be effectively controlled through law enforcement and legislation in Japan. Yago?
Hi, Roland, here. Okay, so that's the $1 million question. I would say the only thing we can do right now is to monitor the products, is do monitoring to find those that are contaminated with chlorinated paraffins. But the most effectively measured would be to guarantee that the Stockholm Convention restrictions are implemented. I think that maybe Roland can confirm that, but I think China has just signed for the IPCP's regulation. Isn't it, Roland?
I mean, China is for sure thinking to ratify short-chain chlorinated paraffins. I have not seen if they have already ratified, yeah. But of course, so I know that in the Chinese Environmental Ministry, there is already one worker, one member, which is responsible to look to short-chain chlorinated paraffins and how China will do the next step on the management. Yeah.
Yeah.
So that is ongoing. Yeah.
That's quite challenging, because the one important thing is to control the production of technical CP mixtures. We are currently working on a study on technical CP mixtures, and we found out that there are some producers, some manufacturers, that they can produce CPs only with a specific chain length group, like only ICCPs or only MCCPs, only LCCPs. But most of the products, they are still a mixture of different chain lengths, and there are some producers that they don't even know that their products contain SCCPs. So it's important to control the CP production in a first step, and also to guarantee that it's regulated under the Stockholm Convention and all the parties are ratifying for SCCPs. That would be easier than trying to monitor all PVC products that are traded worldwide.
Yeah, of course. I mean, the issue is that the paraffins used for the chlorination. So what you see in Europe, yes, I mean it's possible. I mean, for our studies in the oven, for example, to produce clean medium chain chlorinated paraffins, but on the other hand, medium chain chlorinated paraffins are likely also POP. Yeah, so at the moment they are moving to the long chain chlorinated paraffins, but already, let's say, there are studies which also show that long chain chlorinated paraffins are found in biota. The first presenter of our second part of today is Mr. Agustin Harte from the Basel, Rotterdam and Stockholm Convention Secretariat. The Secretariat is guiding the POP reviewing committee process of the new suggested POPs. So therefore, he knows best what kind of information have been compiled for Dechlorane Plus in the POP reviewing committee process. Mr. Harte has worked before more than 10 years in the Ministry of Environment and Sustainable Development of the nations of Argentina. And he will inform about Dechlorane Plus and also the exemptions of Dechlorane Plus in the Stockholm Convention, in particular in respect to plastics. Yeah, please, Agustin, the floor is yours.
Thank you very much, Roland, for the invitation and that introduction. Just before starting my short presentation, because this is going to be a very brief presentation, somebody was asking about China. China just ratified some of the amendments, pending amendments of the convention. As you know, China is one of the 20-something countries that are opt-in. So once chemicals are listed, these countries have to go again through the ratification of these amendments so that the obligations under these new listed chemicals apply to them. And China on the 8th of March, so it's around a month ago, ratified the amendments for hexachlorobutadiene, pentachlorophenol, polychlorinated naphthalenes, deca-BBDE, and short chlorinated paraffins, as well as hexachlorobutadiene. And for China, that will enter into force in a couple of months, in June. But they still have the option, of course, to inform and request to the register of specific exemptions that are still available for some of those chemicals. So we will have some further information on China on the upcoming months. What I can tell you is that the discussions that we had with them is that, well, they were closing the production, this new clean production policy that they are developing some of these chemicals. Just for those who were wondering what was the status for that. And thanks a lot. I've been hearing the past presentations, very interesting. I would briefly go through the proposal for Dechlorane Plus as one of the candidate POPs that will be addressed at the next COP. I will give some further information on that in my last images. But for those who are not familiar on how the process of selecting new POPs and listing them under the conventions are, just quickly, Article 8 of the Stockholm Convention provides the process for listing new POPs, new chemicals or group of chemicals under the Stockholm Convention, and it all starts with a country's proposal that is presented to the Secretariat. The Secretariat does initial screening to see if all the necessary information on the chemical identity and the criteria listed in Annex D of the convention are well presented. And then from there, the process starts under the POPROC, the POPs Review Committee, which is a scientific body under the Stockholm Convention, subsidiary body that revises this proposal and prepares a couple of documents and decisions. The first one is the risk profile that is described in Annex E of the convention. Once the criteria is fulfilled, sorry, the first one is the Annex D, the screening criteria, and then the POPROC works on the risk profile, and finally the POPROC addresses and prepares a document named Risk Management Evaluation, which if the members of a POPROC consider that this should be listed under the Stockholm Convention and global action is warranted because of the adverse effects of these chemicals, or group of chemicals, then the POPROC will recommend to the COP to list this chemical. And usually when the recommendation from the POPROC comes, the next COP decides on listing these chemicals, sometimes with particular exemptions or acceptable purposes. So more or less, if everything goes well, it should take 4 years. The POPROC meets every year. But of course, and Roland has already highlighted that some of the chemicals have taken much longer than that to be listed, mainly because of lack of information or specific aspects of the chemical's nature and impacts missing, so that the decision and action can be taken at the global scale. So for the Dechlorane Plus, this was a proposal submitted by Norway a few years ago, and discussion started within the POPROC meeting in 2019, POPROC 15. Norway proposed to list Dechlorane Plus and both its syn isomer and anti-isomer, so there are 3 cast numbers within the list, and the technical mixture of Dechlorane Plus well, actually contains these two stereoisomers in different concentrations. The commercial mixture is used because it's still produced and used in many applications as a polychlorinated flame retardant, and the use is widely spread, and I will talk a little bit more on the applications. But evidence on environmental monitoring has identified the presence of Dechlorane Plus in the different environmental matrices in a global ubiquitous distribution, even in remote areas. And the nomination made by Norway had good information on the persistence criteria and the bioaccumulation, adverse effects, and long-range transport, which are the 4 Annex D criteria that I was mentioning. So the Dechlorane Plus was used mainly as a flame retardant, and in a lot of applications of different thermoplastics, including nylon, polyester, ABS, plastics, rubber, polybutylene terephthalates, PBDEs, but also in thermosets such as epoxy and polyester resins, polyurethane foams, polyethylene, so several applications as a plastic additive and a flame retardant. One of the highlights is that Dechlorane Plus actually was marketed as one of the replacements of the PBDE that Roland was presenting. So this is a concrete example of what we call regrettable substitutions, when we stop using one chemical and we choose another one which has similar or even worse effects on the environmental health. So we need to start learning from this once and for all. And finally, just for some of the information that was presented in the dossier, some of the trade names that were present and that you could find in the market, Dechlorane Plus 25, 35, etc., depending on the chlorination level and the constitutions of the different isomers. Regarding the production, an estimated of almost 6,000 tons per year as top globally, so around an average of 2,000 tons per year produced globally. The main producers, the US, has been producing this for a long time, but it hasn't been reported in the last years. And the production there was around 500 tons per year. And the only main identified, producer is China as well, reporting around between 300 and 1,000 tons per year. But China has informed that they will stop the production on the 2026, so they will stop producing these chemicals in a couple of years, and hopefully that will also take out the availability of this chemical in the market. In the dossier and the information discussed by the experts of the POPROC, emissions of DP have been identified in several stages of the life cycle of the Dechlorane Plus. One of the most relevant places for emissions was actually the manufacturing of DPs. So there have been some studies, and I gave references in the previous slides on monitoring on the sites where the manufacturing production of the Dechlorane Plus was done. But also one of the other highest releases hotspots was places, for example, where dismantling and recycling of e-waste or end-of-life vehicle was held, and also landfills and open dump sites. So those were the main hotspots for the Dechlorane Plus emissions. But some studies also identified end-of-life products facilities, as well as other places where articles were sold and stored as also part of relevant for human exposure. For example, there was measures on indoor dust that contain high levels of Dechlorane Plus. So for the process of listing, as I mentioned, the discussions under the POPROC started in 2019, where the Norway proposal was evaluated against Annex D. The POPROC concluded that Dechlorane Plus met the criteria, the screening criteria listed in Annex D. So they created an intersessional working group that started preparing the draft risk profile, which, as I explained, is listed under Annex E. And the criteria for the risk profile is listed in Annex E. And so in POPROC 16 in 2020, the risk profile was discussed, but the group couldn't reach a consensus on the decision of adopting the risk profile, mainly because there were some lack of information. Some of the members were asking more information on adverse effects, so that could be considered as a POP. In 2022, after the POPROC convened again after COVID, Dechlorane Plus was considered again, with further information provided by the proponents and other parties that provided information. And with this, the POPROC reached consensus and adopted the draft risk profile and started developing the risk management evaluation, which was also addressed last year at the end of the year on POPROC 18, where the POPROC adopted the risk management evaluation and recommended to the COP to list Dechlorane Plus with several exemptions that I will focus on in a minute. So this is the COP document that will be considered next week at the COP, with a proposal or recommendation for listing Dechlorane Plus with specific exemptions of production as allowed for parties listed in the register, with the provisions of Part 11 of annex of the annex, which I will show in a minute, and for the use in different applications, including aerospace, defense applications, medical equipment, and replacement parts. And we had a discussion where it should be replacement or spare parts, but replacement parts of many different applications. So as you can see here, maybe it's too small, but I've shared the link. You will have the link in the presentation for the specific COP document, but this is the complete listing of specific exemptions proposed to be considered at the COP. So for some of these applications, specifically for aerospace, space and defense applications, and medical imaging, there's a proposal to have a 5-year exemption. Usually when countries apply for these 5-year exemptions, then they have the opportunity to request 5 more years. And then for the replacement parts and repair parts, the exemptions will then apply until the end of service of these articles, or 2044, whichever comes earlier, as agreed by the POPROC. Again, this is a proposal made by the POPROC, and all these exemptions will be discussed and negotiated at the COP as well. So this might change as compared to what could result from the decision at the COP. So again, for aerospace, space, defense, motor vehicles, where 60–70% of the Dechlorane Plus is used in those kind of applications. Industrial machines, forestry, marine and other types of power equipment, medical devices, and other instruments for measurement and analysis. Well, all of these have been highlighted by POPROC members or observers attending the last POPROC discussions. And so this gives us a very good picture of all the different applications that that the Dechlorane Plus is being used for. And again, this came out as a recommendation from the POPROC. Not many of these exemptions were considered initially, but rather came in a later stage of the discussions. And the COP, then we will need to decide on whether these exemptions are still needed, or if there is enough replacements and alternatives for these types of applications. Just to close my presentation and to give you further information on what's going to happen on the following weeks. This is the schedule for the first week of the COP. The COP, as you may know, is a triple COP, the Conference of the Parties for the Basel, the Rotterdam, and the Stockholm Conventions together. It's 2 weeks of negotiations, and that will start next Monday. The regional preparatory meetings are the day before, on Sunday. So Monday, the 1st of May, the plenary will open, and after the morning session, the technical discussions will be held within the contact groups. The discussions for listing of POPs, there are 3 candidate POPs that will be considered at this COP. Will start in a very early stage on Monday, and we expect, if everything goes okay, that for Thursday, 4th of May, so it's 4 days of discussions, the proposals for listing these chemicals will be ready to be considered by plenary and the decision to be adopted. So the first week will be heavily loaded with Stockholm Convention negotiations. I'm leaving here also the link to access all of the COP document, and there you will find the proposal for listing of these and the other chemicals that I think we have a short presentation after me. And just for your information, since you might be interested on having further inputs from experts on these chemicals proposed for listing, the BRS Secretariat has organized also a workshop. It's going to be tomorrow. It's a webinar that the exemptions on Dechlorane Plus and UV328 will be discussed a little bit more into depth. So everybody's invited. I'm leaving the link to register and the link on the website as well to further consult on this information. You will find there fact sheets that the Secretariat has prepared on the main information on these two chemicals proposed for listing. And with this, I close, and I will be happy to respond to any questions if there are any. Thank you, Roland.
Yeah, thank you very much, Agustin, for the insight from the BRS Secretariat. And we will then see next month for the listing, what will be the final exemptions. Questions and answer will be at the end of the session. Okay. So therefore, we had now presentations on brominated, now 2 presentations on chlorinated flame retardants and additives. And as a third part, now we come to the fluorinated chemicals. So the next presenter is Professor Ian Cousins from Stockholm University. He's also a member of the IPCP. Professor Cousins is working since more than 20 years on per and polyfluorinated alkylated substances, PFAS, including also the POPs, PFAS, and one of the key experts in these fields in the world. He will do an introduction to fluorinated POPs, PFOS, PFOA, PFXS, but also other PFAS related to polymers and plastics.
Thank you, Roland. Yes, I'm going to talk about fluoropolymers and side chain fluorinated polymers and the relevance of fluorinated POPs to these polymers and plastics. Yes, so this is the outline to my talk. So I'm going to give you an introduction and overview of different PFAS and different types of fluorinated polymers. And then I'm going to spend quite a long time talking about fluoropolymers and a little bit less time about side chain fluorinated polymers. And I'm going to spend a very brief amount of time, because Roland asked me to talk about fluorinated high density polyethylene containers. And then I'll finish with some conclusions, and hopefully there will be some questions and I can answer them. So this is the overview of the PFAS universe, and it's actually a simplified overview of the PFAS universe. And the first sort of division that we do when we consider the PFAS universe is to divide them up into non-polymeric PFAS and polymeric PFAS. And the non-polymeric PFAS include perfluoroalkyl carboxylic acids and perfluoroalkane sulfonic acids, which are abbreviated to PFCAs and PFSAs, and those are the white boxes on the left. And these are actually the only PFAS that are listed as POPs, and there's only 3 of those, and we'll talk about those later: PFOS and hexane sulfonate and PFOA. And on the right, you have the different kinds of polymers, and I'll just dive into these different sections. The PFAS universe is very large. It's depending on how you count, there can be something like 12,000 substances included in the PFAS universe, but it can be many more depending on how you decide to define PFAS. If we dive into the non-polymeric PFAS, and you look on the bottom left, these are the PFAS listed in the Stockholm Convention. So as I said, PFOS, PFOA, and the hexane sulfonate, and their related compounds. And by related compounds, we mean substances which can degrade either in the environment or within organisms and degrade into these acids, PFOS, PFOA, and hexane sulfonate. And you can see the structures of the PFOA in the middle there of this slide. Has 7 polyfluorinated carbons and a carboxylic group on the end. And these come in different chain lengths, these substances, so they can be anywhere from just 1 fully fluorinated carbon up to greater than 20 fluorinated carbons. And then you have PFOS below it, and the difference there is you have a sulfonate group on the end rather than a carboxylate group. But you also have 8 fully fluorinated carbons connected to a sulfonate group. And these substances, we call them legacy PFAS really these days, because in most parts of the world, they have been phased out by industry, and they've been replaced with other things. So on the right, you have some typical replacements. On the top right is one of the replacements for the use of PFOA in fluoropolymer manufacturing. There'll be a lot more about that later, but this one's called HFP-ODA or Genix. And this one has also been under the spotlight quite a lot. And then you can see below that the perfluorobutane sulfonic acid. So when 3M phased out the C8 chemistry, they phased in instead C4 chemistry. And the idea of both of these replacements was to get rid of the bioaccumulative components. So the POPs, of course, they have to be a POP, they have to be persistent, bioaccumulative and toxic, and PFOA and PFOS meet all those criteria. And these substances on the right, they're also very persistent and mobile in the environment, which is also causing them to be a problem, but they are not bioaccumulative. So they were considered to be suitable replacements. And in fact, now we realize that they were probably regrettable substitutions. In the bottom right, I mentioned also that some of the longer chain perfluoroalkyl carboxylates, C9 to C21 PFCAs, are being evaluated in pop rock for their pop properties and possible listing in the convention. Now, these should also be bioaccumulative because they have longer perfluoroalkyl chains. So we look at the polymeric PFAS, then we have here just three main categories. And altogether, we call these fluorinated polymers. And these are polymers which have one or more monomer units containing fluorine in the backbone or in the side chains. And so the fluoropolymers, this is, in this case, this is PTFE, which is well known by its trade name Teflon, polytetrafluoroethylene. This has fluorine in the backbone of the polymeric structure. That's why fluoropolymers are different from side chain fluorinated polymers on the right, where you have a hydrocarbon polymer or copolymer in the backbone, and then you have fluorinated side chains coming off this backbone. And these fluorinated side chains can be of different lengths. Historically, they were typically 8 fully fluorinated carbons, and then they were replaced with polymers containing side chains with 6 or 4 fully fluorinated carbons. And the middle category is where you have these repeating units of perfluoroalkyl ethers, and we're not going to talk about those today because they don't have relevance for the PFAS POPs. But we're going to talk a lot about fluoropolymers and side chain fluorinated polymers. So fluoropolymers of all the different PFAS, they're one of the most produced, and this is a figure from a paper reviewing science of PFAS, and you can see that they, if you start with the starting components for making PFAS, and you can see that by far the biggest is products that are produced are the fluorinatic acids, and then second are the fluoropolymers, and then quite a long way after that you have all of the side chain fluorinated polymers and lots of other PFAS in much smaller quantities. So fluoropolymers are really quite important in terms of production volume compared to the other PFAS. And also is one of the reasons why industry is so keen on protecting this. This is a relatively high production. And this was just ballpark figures in this diagram from science, but the numbers are actually for fluoropolymer consumption is about 320,000 tons in 2018 per year. Yeah, so, and fluoropolymers are used because they have very special properties, physical properties. They have low surface energy. They're very good at repelling both water and oils and fats, basically a whole wide range of different polarity of liquids. They're very stable, inert substances. They have heat insulation, thermal conduction, dielectric properties, and they can withhold a lot of stress and strain and wear and tear. So they have a lot of use. We've become quite dependent on them in societies. They're used in a wide range of different. We're quite familiar with a lot of the consumer product uses, like non-stick cookware. for PTFE and also barrier properties in things like waterproof clothing, waterproof shoes. But they're actually used much more in industrial uses. And I think this is where industry is most concerned regarding the restriction proposals in the EU, where they're so widely used now in industry in many different applications. And you can find out numbers about, how much is used in different sectors. This is from the Plastics Europe website. You can see there are different uses in, for example, transport, chemical and power, cookware, electronics, etc. So they are very widely used in quite high quantities in many different sectors. And this was confirmed also when Martin Scheringer's group looked at the uses of PFAS, and they identified 200 separate uses for more than 1,400 different individual PFAS, and they noted that polymers dominate the uses. You can see the light blue here are the polymers, and actually the use of fluoropolymers in the production of plastic and rubber was actually the #1 use of fluoropolymers. So a little bit more about that. There's been quite a lot of talk, as I understand, about additives to other kinds of plastics. And fluoropolymers are actually an additive to non-fluorinated plastics. So PTFE is added as an anti-dripping agent, where it has flame retardant is a flame retardant synergistic agent. It's also an anti-wear agent. It's also used as a polymer processing additive to improve molding and extrusion of non-fluorinated polymers. So if you measure fluorine in a non-fluorinated plastic, you shouldn't be surprised, because it's in there in quite a lot of non-fluorinated plastics as an additive to improve the properties of the non-fluorinated plastic material. So a little bit more of a breakdown of fluoropolymers. Well, they are the biggest, #1 use is the best known fluoropolymer, which is PTFE, which is more than 53% of the consumption. And then the second is PBDEs, polyvinyl iodine fluoride, and that's actually used a lot in lithium-ion batteries, in the electrodes of lithium-ion batteries. And so the production of PBDEs is really increasing, and it could even overtake PTFE in the future. And you can see some of the major companies, some of the well-known companies in the fluorinated chemistry business here that are really dominating. So well-known companies like Chemours and Solvay, Arkema, and so on. But also very much in China now, the Shandong Dongyi group now also starting to increase the slice of their pie there. And as I said, 320,000 was the 2018 number for consumption. You can see it's split between the different countries, with China dominating now the consumption. A lot of these companies like Chemours and Solvay are actually operating in China as well as the Chinese companies. And you can see here again, that's just as a pie chart with China dominating the production of fluoropolymer. And the trend you can see from this paper called The Promising Future of Fluoropolymers is optimistic that we will continue to keep producing more and more fluoropolymers into the future. So that's at least what the industry's view of how things will go forward with fluoropolymers. So back to the relevance of fluoropolymers to the Stockholm Convention. And so the main relevance here is that the salts of perfluoroalkyl carboxylic acids, specifically the ammonium salts of PFOA and PFNA, were used as processing aids in the polymerization of certain types of fluoropolymers, mostly historically, but in China, this continues. So the ammonium salt of PFOA and is used still in China for making PTFE and even other fluoropolymers. And the result of this use was a huge release of PFOA and PFNA to the environment, because in the past and currently in China, this emission is not really well controlled. A point actually is that not all fluoropolymer manufacturing requires these polymerization aids, and I'll explain a little bit more. It's only this process of emulsion polymerization. So if you make PTFE by suspension polymerization, you don't actually need these. fluorinated processing aids, but you only can make certain types of PTFE with suspension polymerization. So you do need to use emulsion polymerization for making, say, the fine powder PTFE. And there's also been, like historically especially, there were residuals of PFOA and PFNA in a lot of fluoropolymer products and other PFAS as well. Now that's got a lot better in recent times, and I'll explain more about that. But PFOS and hexane sulfonate were not used in fluoropolymer manufacturing. So there we can forget the relevance for these substances, but they are very relevant to the side chain fluorinated polymers, which I'll come back to later. So more about this, why you only need fluorinated surfactant processing agents when you make certain types of PTFE. So when you make granular PTFE, it has larger particle sizes, then you can use suspension polymerization. You don't need any surfactant processing aids. But when you make these fine powders and these aqueous dispersions, then you have smaller particle sizes, and in order to make these finer powders and aqueous dispersions, you need to have use the process of emulsion polymerization, which requires a surfactant processing aid. So you need some kind of surfactant usually in this manufacturing process of emulsion polymerization. So you can see it's about 50-50. So about 50% of the PTFE that's produced doesn't require any surfactant, whereas the other 50% does. Historically, there's been wrote this paper in 2005, published late 2005, and you can see that the PFCA emissions, the perfluoroalkyl carboxylate emissions, are dominated by fluoropolymer manufacturing. So something like 80% of the total historical emissions of PFCAs was from fluoropolymer manufacturing. So it's a huge amount came from this one particular source. And you can see the other parts of the pie as well. We did calculate the emissions from the other parts, but they were much smaller, the other sources. And in the case of PFOA here, you can see like 94% of all the PFOA that's ever been emitted up till 2005, when we published this paper, came from fluoropolymer manufacturing. So it was a really important source. And it still is an enormously important source in China. And with huge emissions ongoing there. And it was also, you can see, a very important source historically for PFNA as well in the manufacture of PBDEs. And this has been well documented in this, this movie. This movie is all about fluoropolymer, huge fluoropolymer emissions at the Chemours plant in West Virginia. There's been a lot of research around that, showing that the population around that plant have health effects linked to PFOA. And there's also a lot of concerns around some other plants that have been making PBDF, like in New Jersey, for example, where New Jersey is suing Solvay. But most of these, in most cases now, as a result of the US EPA stewardship program, which was a global stewardship program, a lot of companies phased out the use of these long chain acids. But the exception is in China, which is still been releasing huge amounts. And I'm not going to go into all the research that's been done, but Chinese researchers, we have, and others researchers around the world have documented that there's huge ongoing emissions of PFOA in China from PTFE manufacture. In the rest of the world, the companies have actually tried to phase out PFOA and used other substances instead. So each company has their own kind of processing aid, and so the top one here is Gen X or HFPODA, which is made by Chemours, and then the second one here is another replacement that's used by Solvay. And you can see I put some things in here that these replacements have turned out to be regrettable substitutions, are now under regulatory pressure themselves. So Gen X, for example, is a substance of very high concern now in the European Union. It's now all PFAS are getting restricted in the European Union. So these substances will be under regulatory pressure. The main concern about these is, as I said previously, the idea was that these substances would not be bioaccumulative. But the problem is that they're just as persistent, and they're also very mobile. So they tend to contaminate drinking water and accumulate in drinking water sources. And they're so persistent that they just will not degrade at all. So this ether linkage doesn't help in reducing their persistence. And wherever they've been used, they've been detected now in the environment. So these are some other examples of replacements by different companies. There's one by 3M there, another by Hesai Glass, another replacement by Solvay. All of these have been detected in the environment around these fluoropolymer manufacturing plants, and sometimes they've been detected in remote areas like the Arctic. So they're not considered to be a great replacement for PFOA or PFNA. Now companies have also realized this, and they are replacing these replacement fluorinated processing aids with other replacements. So some companies are actually now phasing in non-fluorinated processing aids. So these are basically non-fluorinated surfactants, which can now do the job. And there's been patents for these non-fluorinated surfactants for the last 2 decades, but it's been taking a long time to actually make these processes operational. But some companies are now switched, like Arkema, GFL, which is Gujarat Fluorochemicals, which is an Indian company, have now switched to using non-fluorinated processing aids. And they tell me that if the non-fluorinated processing aids were now used for making PTFE by emulsion polymerization, that we could actually get to a point where nearly all fluoropolymer manufacturing is conducted using non-fluorinated processing aids in the near future. But I have to say that the industry is split on this. Some companies don't believe that this is the way forward and believe that we should carry on using some of these fluorinated processing aids. And the reason for this is that they say that by using these non-fluorinated processing aids, you actually increase the release of fluorinated byproducts. So you remove one problem and create another one. So some companies say that they're not going to do this, and instead of moving to non-fluorinated processing aids, they think the better thing is to increase the recycling of the surfactant and also the elimination of the surfactant from emissions, so that you can carry on using the fluorinated surfactants, but you eliminate the emissions. So this is, some companies think this is the right approach, and other companies think they should replace the fluorinated processing aids with non-fluorinated processing aids. You can see the industry is really split on this issue. It's not just about the processing aids. There's been a lot of focus on PFOA and PFNA, but there are lots of other fluorinated compounds which are released during fluoropolymer manufacturing. So, for example, it's well known that there can be fluorinated gases released during fluoropolymer manufacturing, and these are also heavily regulated. And these fluorinated gases can have very high greenhouse gas warming potential. There are also oligomers that are emitted to the environment around the plants. And then we find some very strange substances that, like, for example, you find these perfluoroalkyl carboxylic unit acids which have repeating CF2 and CH2 units in their structure. So these are not regulated. And chemicals have actually themselves also confirmed there's greater than 250 different novel, potentially unique PFAS in their effluents. So there's lots of oligomers and other fluorinated byproducts released during fluoropolymer manufacturing, and most of these are not regulated. Just the only things that are really regulated very tightly are the fluorinated gases and the processing aids because of historical disasters. So what's the fluoropolymer manufacturer's position? Well, they're obviously very concerned, as I said previously, that they want to continue using, continue making fluoropolymers because they believe that they're very important for industry. They think that fluoropolymers should be considered as a separate family with regard to regulation. And they say that fluoropolymers meet the OECD criteria of polymers of low concern. They say that many of the industrial uses are essential for health and safety and critical to the functioning of society. And they say that they have addressed a lot of the issues regarding all of the historical issues regarding the releases during manufacture, the residuals in the products, and the problems of the end of life. So that's their point of view. But our point of view, and we have myself and other co-authors have said there are actually quite some issues remaining regarding emissions during the fluoropolymer life cycle. And so we look at the use phase. As I said, the OECD PLC criteria largely focus on the use phase. And so there's been some papers, you can see the publications at the bottom here, by industry saying that modern fluoropolymers contain very low residuals. And it's true. The fluoropolymers in the past contain much higher residuals of these, like these POP-PFAS, like PFOA and PFNA. They sometimes contain larger than 10 ppm, much larger than that in the residuals in the products, which was a concern. But now they spend a lot of effort in cleaning up the products so that they contain very, very low residuals, less than 1 ppm. And that's largely, that's the case for most companies. We don't know if it's the case for all companies because they haven't analyzed all products from all companies. It could be that some companies, for example, Chinese imported fluoropolymer products may contain higher residuals. We don't know. We just haven't done enough analysis to really have a really good idea about the residuals in all types of fluoropolymer products. There is an issue of overheating, for example, cookware. If you overheat the Teflon pan or PTFE pan, you have to go above 250 degrees, which is very unusual, but it can happen. But you can get mostly just the short chain PFCAs produced in the gas phase above your pan, not the longer chain POP-PFAS. And when we talk to industry about this, they say follow the normal operating procedures. Regarding end of life, what happens to the fluoropolymers at end of life? Well, this is information again from industry showing the collection of plastics and the fluoropolymers. And you can see the fluoropolymer is actually quite a low percentage of the plastics. And this is also pointed out by industry all the time as an excuse for being, that fluoropolymers are actually very low volume compared to other plastics. So, when they are released to the environment, then it's trivial compared to other plastics. That's often, I've often heard that as an excuse. But what happens to the fluoropolymers? Well, most of it gets incinerated. Very little gets recycled because it's costs too much money to recycle fluoropolymers. They're quite often used in very small quantities in complex multi-component things like a phone or a car or something. It just isn't economical to recycle a fluoropolymer. Most of it is incinerated, or there are other recycling processes like metal recycling. What happens during incineration? Well, the most comprehensive review is from RIVM, and they show that PTFE basically breaks down, but mineralization is uncertain at typical operation temperatures. So it's most likely that there'll be some small fluorocarbon gases that will be released. That could be strong greenhouse gases, but there's no evidence of any POP-PFAS being released from incineration of fluoropolymers. But there's international research going on this right now to better understand the emissions from incineration of fluoropolymers. And it's really uncertain also regarding what happens if you do metal recycling, which happens at lower temperatures. Maybe then there could be other things released. So I'm going to move on to side chain fluorinated polymers. As I said, these are polymers with non-fluorinated polymer backbone, and they have these fluorinated side chains. And from this report on the right here, there was a non-exhaustive list of about 103 side chain fluorinated polymers and 42 PFAS monomers. And the non-fluorinated polymeric backbones can be acrylates, urethanes, oxetanes, ethoxylates, and many other things. It's very difficult to identify the exact structure of these because it's confidential information. But we have a rough idea, but not really an exact idea of what the structure of these side chain fluorinated polymers are. Now, they're used in much lower quantities than the fluoropolymers. We don't know exactly how much, but it's kind of an order of magnitude lower. And they've been used in surface treatments. For example, on the outer weave of your, say, your waterproof jacket, you would have had those, historically, if it was a fluorinated one, you would have side chain fluorinated polymers to give you water protection, durable water protection. They're also used in carpets to give you water and stain repellency, and also just a lot in food contact paper, especially historically in, for example, microwave popcorn and pizza boxes and so on, anything where you have fatty foods, even candy wrappers, butter wrappers, at least historically. And they were also used as fluorosurfactants in a wide range of uses. So they have like I say, they have different kinds of non-fluorinated copolymers. So the structure A here is an acrylate and the structure D is an ethoxylate. They can be fluorotelomere based. So the structure A here is a fluorotelomere based side chain fluorinated polymer, and the structure D is a perfluoroalkyl sulfonyl fluoride based side chain fluorinated polymer. And these were made largely by a company called 3M, these BASF based ones. And then these fluorotelomere ones were made by companies like Chemours, but many other companies as well. And the fluorinated side chains historically used to be mostly 8 fluorinated carbons, and then they were phased out and replaced by side chain fluorinated polymers with usually 6 in the case of Chemours and 4 in the case of 3M. Carbons. And yeah, so in terms of historically, these were hugely important for the PFAS. So the use of these by companies like 3M that used that made a lot of these C8 based side chain fluorinated polymers. They were used a lot in food contact materials. And it's considered that they didn't just contain PFOS, they also contained PFOA and hexane sulfonate, and that this could have been a very important historical exposure source, human exposure source. But these largely been phased out now. And this is probably why we see a big reduction in the levels of PFOS, PFOA, and hexane sulfonate in human blood over the last 20 years since 3M phased this out from food contact materials. But historically, this was a huge deal. A lot of these polymers still remain in the environment, so they can still act as a source, even though they were phased out. They can still be in landfills, they can still be in soils. These side chains, there's been quite a lot of research on how easily they cleave in the environment, and they don't cleave very easily under environmental conditions. The major problem with these products was not the cleaving of the side chains, it was all of the impurities that were in the products. So they contained a lot of the acids impurities, but they also contained a lot of precursors in there, including monomers and things, which can leach out the product or degrade in the product and produce even more acids, which can then leach out. So that was the major source, not the cleavage. The cleavage, if the cleavage happens, it happens over a decade kind of timescale. It could be an important source in the long term, but it wasn't the major source when they were used. Yeah, so these historically, these PSF-based side chain fluorinated polymers, they contain 8 fully fluorinated carbons, and so they contain PFOS, hexane sulfonate, and PFOA, and the precursors in the products as impurities. And the fluorotelomere-based ones contained 8 fully fluorinated carbons, and they contain PFOA plus a whole range of other PFCAs and their precursors in the products. But the modern side chain fluorinated polymers, which are used, they are still used, although in less quantities than previously, they have 4 fully fluorinated carbons or 6 fully fluorinated carbons, depending on which company. 3M are getting out of the business, so there won't be so many of these 4 fully fluorinated carbon products in a couple of years, but there still should be some of these 6 fully fluorinated carbons on the market. And they're very specific now, whereas before they contained a whole wide range of different chain lengths. They don't contain much above 6 polyfluorinated carbons, hardly any impurities above 6 polyfluorinated carbons, very, very low. So they're 6 or lower. So as I said, these side chains do not cleave off very easily. There's been quite some research, and they take several decades, but it can still be an important long-term source because these have been shown to be sitting in soils and landfills. So even if they slip, we've done some modeling work, and it can become a significant source, even if it takes 15 years or so for these side chains to degrade. So the emissions from these side chain fluoropolymers. So during the application of the formulations, that say textile mills in China, for example, or in other parts of Asia, there's quite a lot of releases of these during the manufacturing process. And then there's also a lot of release during use and disposal of treated articles. So in the use phase, every time you wash your waterproof jacket, you are releasing perfluoroalkyl acids into the environment, in the wastewater. There are also quite a lot of, like I said, there's a lot of these polymers sitting in soils and sediments and sludge, landfill leachates, and these can be a long-term source of the perfluoroalkyl acids in the environment. This is one of the reasons we don't see big declines in some of the PFAS, because we still have this slow release of these substances from the environment. Yeah, and in regard to the modern ones, which are based on C4 and C6, these are going to be, there's going to be a release still of these during their life cycle, the butane sulfonate and hexanoic acid, but as I said, negligible long chain impurities in these products. Roland asked me to briefly mention this before I go to the conclusions, and I've just said this is a special category. They're not technically fluorinated polymers because they're not like fluorinated monomers with repeated units. Instead, it's a non-fluorinated plastic, which is then is treated with an inert gas mixture, fluorine gas mixture, and to get a thin layer of fluorine on the plastic surface to add extra protection to the plastic material. And there's been some focus on these special kind of containers, and it's been shown that there is leaching of perfluoroalkyl acid, including hot PFAS, PFOA, and longer chains that can leach from the containers into food. So this is currently an area under investigation. So this is a very special category. So conclusions, fluoropolymers are used in very large quantities compared to the side chain fluorinated polymers. There's industry pressure to separate them from other PFAS and to continue, so we can continue using them in a wide range of different applications. It's true they're widely used in society now, including in industrial uses, and it can be challenging to find alternatives for some of these uses. But there are also concerns remaining regarding the Chinese emissions of PFOA that were ongoing. They're also using other substances which could probably have hot properties, like this HFDO trimer acid, which has been shown to be bioaccumulative, persistent, and toxic. But this is used really exclusively in China, but it's a problematic substance, and China isn't a small country. Companies continue to emit these PFAS processing aids in the rest of the world, the replacement ones. But the emissions are controlled more and more, much more tightly than they were in the past. And non-fluorinated processing aids are being phased in by some companies. But there's quite lack of information sometimes on the other PFAS emissions. So I talked about all these other hundreds of potential substances that can be emitted during fluoropolymer manufacturing, which are not regulated and we don't have much information on. And there's also some question marks remaining in the end-of-life emissions. So the conclusions for the side chain fluorinated polymers. There's a wide range of the different kinds that being produced, much smaller quantities than the fluoropolymers, but in the kind of 10,000 tons globally per annum. There are a lot of different non-fluorinated polymeric PFAS present in the side chain fluorinated polymers, sometimes in quite high levels, including and also precursor materials which can degrade into perfluoroalkyl acids. and substantial amounts of these acids can be released during the life cycle. Historically, a lot of POP PFAS were released. And there's some question marks regarding the degradation of these side chain fluorinated polymers, these side chains, and how important that could be in the long term for the slow release of some of the perfluoric acids. So that's it. Thank you for your attention. I realized that was a lot of information, but hopefully it was useful and that you can have some questions.
Yes, absolutely, Ian. So thank you very much to make the link between plastics, polymers, and this fluorinated POPs. So it was a great presentation. And yes, I know you are also a very busy person. So we maybe take the questions directly what we had. So one question is, does these fluoropolymers relate to any ways to fluorinated gas, as I'm looking from the greenhouse gas perspective? I think you already mentioned a bit, but maybe you can elaborate a little bit more.
Yeah, these are quite well regulated. The fluorinated gas emissions, I don't know a huge amount about it, but I know that the fluorinated gases emitted, including greenhouse gases, emitted from fluoropolymer manufacturing, and this is one area that is regulated. You know, I mentioned that the processing aids, things like PFOA, ammonium salts of PFOA, these were well regulated, but so were the fluorinated gases. So it's something that that has been looked at and regulated, but there are lots of other fluorinated substances that are emitted that are not so well regulated.
Yes, then another question was, what are the adverse effects of this PFAS? So maybe only short, I mean, this could be another hour talk.
Yeah, well, to actually prove the effects, I mean, they've done some, the most famous one is the study in dark waters, which is where they actually got tens of thousands of people to donate their blood, and then they could do very detailed epidemiological studies of the effects of PFOA on the population, and they found links to 6 different diseases, including 2 types of cancer, the testicular and kidney cancer, but also diagnosed high cholesterol, thyroid disease, and there's links, mechanistic links, so they see the same effects in animals. When they do like animal testing, so you see the same effects on the population level as you see in animal testing. So there seems to be very good evidence that high, elevated exposure to PFOA causes these effects. The effect that has driven the drinking water guidelines now is immunotoxicity. So they're suggesting, again, from human studies that were conducted first on the Faroe Islands, that elevated exposure to PFAS can actually reduce your ability to produce antibodies against some well-known diseases that children are vaccinated against. So, for example, tetanus. So it's, this has driven the drinking water guidelines down even lower.
The immunotoxicity, the decrease of, the immune system of children's suppression. And yesterday I mentioned also that there are some studies in respect to sperm quality, Denmark, Italy. Yeah. Okay, then there was a question, could you expand a bit more on the mechanism of releases from side chain fluoropolymers, specifically about impurities of the acids and precursors? How can we measure the long-term effect of this leaching from products?
Yeah, the mechanism is like the acids will wash off because they're quite water soluble. So they can leach off quite easily, the acids from a product. So if you wear a jacket and it rains, they can just wash off. Or particularly if when you wash your jacket and you're going to have, or your carpet or whatever, you're going to release these water soluble ones. Some of the precursors are quite volatile. So things like fluorotellular alcohols can just volatilize off your jacket. So it's well known that people who work in, the levels in, say, outdoor clothing stores, in indoor air and outdoor clothing stores are much higher than they are in other indoor environments, because you have a lot of volatile chemicals being released from the products in use. So so these are two different mechanisms that can, and then there's the long-term possible degradation of the side chain, because most of the releases are these impurities that are in there, which are not actually doing anything in the product. They're just sitting in it. They're just impurities in the product that were made. They're there during the manufacturing process, but then can be released during the use of the product. And so it can be water-soluble or volatile substances, which can then be emitted. And how to control them? Yeah, I mean, if they're in a landfill or there's not much you can really do.
Yeah. And there's a good study,
this.
from EPA, Washington et al., 2013, 2015, about this long-term release, where they calculated half-life time for some of those up to 130 years. So yes, that's a real issue. Ian,
you can have leachate treatment. A lot of landfill sites now are introducing leachate treatment on the landfills so that they can remove the long chain perfluoric acids from the leachate. And this is quite expensive, but it's it kind of has to be done if you want to stop the acids from the landfills entering the environment.
Yeah, which will be a huge challenge for developing countries. It's quite costly. Yeah. Can you stop sharing your screen? Because for one question, I can share this one, because there was one question about the human exposure to these substances. And there, I have also made this kind of slide similar to the other ones, where you see the differences of PFAS compared to other POPs I showed. Yeah, so because PFAS are water soluble, so they have on one hand, yes, the normal accumulation in kettles, yeah, and chicken eggs and so on, but also there is the exposure from the water way. This means we can have a direct exposure from drinking water, from groundwater, yeah, from surface water. And then, unfortunately, these PFAS are the only POPs which really directly can go into plants. Yeah, and from the plants, either you can have direct food contamination, including fruits. So here the short chain PFAS are also more accumulating in plants compared to the long chain PFAS. And then also from the plants, we can have accumulation from the plants to the animals. Yeah. So therefore, with PFAS environmental release, and we have a range of direct exposure then to the population. And additionally, like I showed yesterday, also from PFAS, we can have exposure from products like carpets, indoor, to the dust, where a US study showed that this can be also a major pathway of exposure of humans also from products. So with PFAS, this exposure pathways are more complex and are.
I can just add, Roland, that it depends on the PFAS. So for PFAS, it's meat and fish are very important exposure routes. But if you when you go to the shorter chain substances, then water and vegetation is much more important. So it is really specific on the particular PFAS, which pathways. But you can't avoid the exposure, whatever PFAS you will get exposed one way or another. But the pathways change a little bit depending on the PFAS.
Hey, yeah. So again, thanks very much. We come now to the last presentation of today. So the next presenter is Mr. Narain Asta from the Swiss EMPA Institute, and he will give an introduction to the POP candidate UV328 in plastics and suggested exemptions for use in plastics. He has been involved also in the POP reviewing process of assessing UV328 for the listing in the Stockholm Convention for the Swiss Environmental Ministry. And currently, yes, he makes his PhD at ETH Zurich in cooperation with EMPA on microplastic in the environment. And also he is an author of the Chemicals in Plastic report for UNEP, where I'm really grateful for your good help, Narain, the last more than a year. So you can start to share your...
Narain, and I'm working at EMPA. And I will talk to you briefly about UV328 and its uses in plastics, as well as some of the exemptions that were requested by industry during the POP-ROC process, so the POPs nomination process for UV328. And basically, if you look to the right, you can see the chemical structure of UV328. It is a phenolic benzotriazole, so it has a phenol group on the right and the benzotriazole group on the left. And what it does is basically it can absorb the full spectrum of UV light, so 250 to 400 nanometers wavelength, and therefore it's used as a UV absorber in different materials, including plastics, but also paints. I won't talk much about paints and coatings in this presentation, but I will focus on its use as an additive in plastics. One thing to note is that it's not covalently bound to polymers, and so it has the potential to be released from plastics and be taken up by, either released to the environment or taken up by organisms. Depending on the different polymers, it has different application concentrations. It's used in really a wide variety of polymers, all the way from polypropylene, polyethylene, PVC, rubbers, elastomers, resins. And typically its recommended loading is between 0.1% and 3% by weight. But depending on the specific polymer, it requires different amounts. So you can see it's typically in some of these common polymers, it's less than 1%. And there are some studies that have also looked at products containing, they have looked at UV328 in products, and these are recent newly produced products, and they have orders of magnitude lower concentrations. So it could be that due to the upcoming regulation, people have stopped using it as much, or there are maybe impurities in products. But basically, yeah, 0.1 to 3% by weight is typically loaded. Just to give you a quick overview, and I'm not sure if it was covered previously, but UV328 is listed as a substance of very high concern in the EU since 2014, and it's also regulated under European REACH regulation since 2020. So it's currently mainly produced in the US and Asia. In 2020, Switzerland proposed its listing as a POP, and last year at the last POP-ROC's meeting, the POPs Review Committee recommended to the Conference of Parties that UV328 be listed in Annex A to the convention. So global elimination with some specific time-limited exemptions, which I will cover a bit later. So there are some reported uses of UV328 that are relevant to plastics. It's commonly used in packaging materials, especially transparent packaging films, as well as including in food packaging, specifically in the non-food contact layer. It's also used as an additive in printing ink, in plastics and rubber. It's also widely used in the automotive sector, so pretty much any part of the vehicle that will be exposed to the sun may contain UV328, as well as some of the displays that are inside the inside vehicles. Then it's also used in electrical machinery and equipment. So if you think about anything related to light, so LCD panels, LED panels may contain UV328. UV328 is also present in, typically used in photographic paper and polarizing film. because it can prevent the fading of color of these materials. And finally, it's also applied in textiles, but it's not clear how much of it is used. And as with many of the chemicals, we don't know exactly which products contain UV328, but we have a general idea of what types of applications it's used in. There are also some monitoring studies that looked for UV328 in consumer products. And as one would expect, UV328 was found in different packaging materials. So milk packaging, snack packaging. But also of concern is that, it was found in recycled PET intended for food contact materials. And if you remember, the recommended application is for food packaging, but not in the food contact layers. And so this is where it starts to get a bit concerning, and also considering UV328 is an endocrine disrupting chemical. It's the fact that it's been found in toys may be an issue, hair accessories. And IPEN also did a study where they looked at chemical additives of concern in different in recycled plastic pellets from different parts of the world, and they also found UV328 in recycled plastic pellets. And finally, and I think Professor Takada might have talked a lot about this, but UV328 has also been found in marine plastic debris, including in the plastics ingested by seabirds, with subsequent accumulation of this chemical in the seabird livers and different organs. So during the last stage of the POPs nomination process, different industry stakeholders and companies that use UV328, they requested specific exemptions. And so I've marked in dark, in black, which ones relate more to plastics. But basically, the exemptions that have been requested include UV328's uses in land-based motor vehicles, so cars, motorcycles, cranes, trucks, as well as for spare parts for these types of vehicles, as well as for industrial machines, LCD panels in medical devices, LCD panels in measurement devices like infrared radiation thermometers or similar analytical instruments. As I mentioned, I won't go too much into the coatings, but maybe the photographic paper application, even though this is not really plastic per se, there's often a plastic layer on these polarizers films. And basically, these applications will for these applications, the exemptions typically will be following Article 4 of the convention. By default, this is set to 5 years, but unless it's otherwise stated that the exemption will be shorter or longer. So for example, with this legacy spare parts, the exemption is expected to last either until the end of the service life of these replacement parts or the vehicles, or 2044, whichever comes earlier. And just to give you an overview of, and this is for what we have a lot of information about now, but basically, UV328 is really used in different parts of the cars. So all the way from inside and outside bumper systems, radiator grills, polarizing films inside. So for the meters, telling you how fast you're going or the fuel that's remaining. The roofs, soft and hard. So whether it's a convertible car or something with a solid roof, it may also contain UV328. And also in the paints and coatings of these cars. So it's really can be found in a wide variety of these large plastic parts. And industry has estimated that most of it, 99% of it, may be contained in the bumper systems and radiator grills. So that's probably the place to be looking for it in the future. Now, coming to the alternatives that have been proposed for UV328, there are many different classes of UV stabilizers or types of UV stabilizers. They include other benzotriazoles that look similar to UV328 or benzophenones. These have been claimed to have a shorter absorption of UV light, so they may not be preferred in some applications. Then we have hindered amine light stabilizers, which technically do not replace UV stabilizers, but are used in combination with them. And some other classes of UV stabilizers, like cyanoacrylates and oxalanilides. But with these types of, each of them have different hazard profiles or cost efficiencies, cost effectiveness measures. And one thing of concern is that potentially UV328 will just be substituted with another chemical that looks like it. So they include other benzotriazoles such as UV234, 326, or 329, and many others that could, and these three specifically are being considered in the EU for their very persistent and very bioaccumulative properties. So yeah, the situation may not necessarily change, but yeah, this is kind of the overview of the issue with UV328. I think it's being included in a lot more monitoring studies since its nomination, and we will see next week is the conference of parties, and the decisions, specific decisions on this chemical will be made then. So yeah, whatever I presented, all the information is contained in some of these documents that you can access on the Stockholm Convention website. And yeah, thank you for your attention.
Yeah, thank you very much, Narain, for this condensed but on the point presentation on UV328 in plastics and relationship to plastics. I also learned something new. For the questions, we clarified many of the questions. There was one comment from Yuyun about a study they are conducting. Yuyun, are you online? Do you want to inform
Yes.
the audience on your study on PFAS?
Yes, sure. Thank you, Roland. Yeah, we just preparing to release our new report on PFAS in textiles and food packaging, paper food packaging. Some of them are popcorn, microwave popcorns imported from the US that's sold in the Indonesian market from 3 identified brands or producers. And the rest of the samples are textiles that we purchased in Indonesia. It's from waterproof hijab to anti-stain children's t-shirts, and that shows very high PFAS chemicals in the samples of waterproof hijab, which is the highest, about 30,000 nanogram per gram, so ppb. But in terms of PFAS in popcorn chemicals, we found the imported ones from the US are still containing PFAS concentrations, but only one company claimed that they already phase out. So in our study, we also identified that the most detected congeners are 6,2-FTOH, and those are the chemicals that I put on the chat. but it's not easy to recommend regulations for government, especially in developing countries. So my question to Professor Ian, if you're still here, is that some researchers recommended the approach of total organic fluorine concentrations in samples as an approach because due to the limitations of the laboratory capacity. Could you please explain or elaborate more the plus and minuses to use that TOF approach? Thank you.
Yeah, you can, of course, you can do total fluorine on a solid material as well, which doesn't require an extraction step. If you've got something like a combustion ion chromatograph, you can actually, you just have to combust the sample and do a total fluorine. But the TO, when you do extractable organofluorine, then you have to extract the sample in some way, and so there's been some problems maybe with standardizing this method because different labs will have different protocols for doing the extraction step and maybe using slightly different solvents or something. This is so a problem with it at the moment is there's not really a kind of standardized protocol. There's not been enough into laboratory testing. There's been some work in Sweden on applying it to water samples and different labs then comparing with each other to see if they can get the same results for water samples, but not really for consumer product samples. So I think that's one of the big disadvantages of the technique. Of course, it can also, in the case of, it can also give you some false results sometimes, depending on, you know, if you may think that there is, like I mentioned before, you can add fluorine. Fluorine is sometimes added as to non-fluorinated plastic. So we got quite confused when we were looking at artificial turf for quite some time. We started using a total extractable organofluorine for this, and we got very high levels of fluorine in the sample. But it turned out that all of the fluorine in the artificial turf is like PTFE, which is added to improve the extrusion of the blades in the artificial grass. So you don't know. Another disadvantage then is you don't know the identity of the fluorine, so you have to do some additional analytical steps once you've done the TOF to work out what the identity is. So that's another disadvantage that I can think of off the top of my head.
Okay, thank you.
Yeah.
Yes, thank you. Maybe an addition here. For the Stockholm Convention, we have developed a guidance on screening and monitoring POPs in products. And in this guidance, we have compiled also different fluorine screening technologies. So this can also be downloaded. I will also share the link here in the chat on screening methods. Then when we look to other questions, there was one question about infographics. So where can we find infographics for POPs for capacity building? I mean, the Stockholm Convention has materials. Infographics we have included in our report on chemicals in plastic, which hopefully will be published next month. So there we have infographics on the relationships of chemicals in plastic from different perspective. Another question here, which just come in: what is the standard test method to analyze UV 328 in plastics? To Agustin, I don't know, Agustin, if you know that. So these kind of specific question for analysis will be addressed in our next webinars in the second half of May. So there we will have one detailed webinar on analysis of POPs in plastic. This will be actually number 5 of the webinar. There will be one webinar about extraction and cleanup of POPs in plastic. And also there will be one webinar of sampling of plastic for monitoring POPs in plastic. So Agustin, if you know something about the method analysis of UV 328, you can come in. If not, I recommend you. So we have Fraunhofer Institute from Germany, which are analyzing the UV stabilizers in plastic and are part of our team of monitoring POPs in plastic, and they will present probably in the last week of May also on analyzing UV 328 in plastics, and we will have also a presentation on Dechlorane in plastics, brominated flame retardants analysis in plastics, and also the chlorinated paraffins, which have real analytical challenges. But this is topic of our upcoming webinars. Agustin, do you want to say something?
No, not my expertise, but if we need to find somebody else, we can for sure.
So in our guidance document, so we have analytical methods, but not yet for UV 328 and Dechlorane Plus, but we will present and give a method then in that webinar end of May. Okay, Lisa, do you see any other question? Okay, I see to Ian. What is the bioavailability of the food packaging and monomers?
Fluoropolymers, I believe. What is the bioavailability? Yeah, of fluoropolymers.
Fluoropolymers.
Well, I think it's not really that well studied. I think it's low. I mean, there's been studies where people have been fed PTFE, actually. Humans have been fed PTFE, and it tends to just go straight through. It's low. Of course, there can be impurities, and it's certainly in the old PTFE, there were residual impurities in there, and these would have potentially leached out during digestion and been taken up by the body probably. But the PTFE itself should have very low bioavailability and just go through the body if it's ingested. And I guess we all have ingested some small PTFE particles at some point during our life, probably from wearing of our non-stick pan or something like that.
Okay, yeah, thanks, Ian. So also now our time is up, but I think we were quite on the point. It's just 2 minutes over 4 o'clock. Lisa, do you see another question?
I see no more questions. I don't see any more questions.
Okay, so I have also posted the link to the Stockholm Convention guidances. There are different on NIP update inventories, and under the inventory guidance, you can find that guidance on monitoring and screening POPs in products. So thank you very much to the presenters, for these very interesting and good presentations. Thank you for the audience to be with us for the 4 hours. I wish you good progress, everybody, in their research, but also for policymakers which have listened. Yes, the subject is sometimes quite complicated. So therefore, the science policy interface, and that you have a contact with your scientists, which can help you with this nitty-gritty and can explain you this kind of details than in your countries, sometimes maybe better with your language. I recommend you to participate also then in our webinars in the second half of May. For those policymakers, this will be quite scientific, and it will be really on the monitoring and analysis and cleanup and so on. So maybe for policymakers, you might look that your research community might participate in these webinars then, and you might inform them and forward the link to your research institutions that then in the next step they can learn and then can do a good science policy advice. Yeah, thanks to all. Stay tuned. And yes, hopefully see you next time in our further webinars. Yeah.
Thank you,
Bye-bye.
Roland, and everyone. Bye.
Yeah, Yun, bye.